Right now, there is a point of light in the southern sky that most people have never noticed. It sits just below the constellation Centaurus, unremarkable to the naked eye, easily overlooked beside brighter stars. You could stare at it for an hour and feel nothing. It looks like every other star. It looks like it belongs exactly where it is fixed, eternal, indifferent to your gaze. But that point of light is the closest star to our sun, and the distance between you and it right now, as you sit reading these words, is approximately 25 trillion miles. 25 trillion miles. Write that number out in full and it loses meaning entirely. It becomes abstract. It becomes something the brain refuses to process, the way it refuses to truly comprehend its own mortality. You see the number, you acknowledge it, and then you move on, because there is nothing in human experience that prepares you to feel what 25 trillion miles actually means. So, let us not start with the number. Let us start with light. Light is the fastest thing in the universe. This is not approximation or a simplification. It is, as far as every experiment ever conducted has confirmed, an absolute ceiling, a speed that nothing with mass can reach, and nothing at all can exceed. Light travels at 186,000 miles per second. In the time it takes you to blink, light has traveled roughly the distance between New York and Los Angeles, twice, in 1 second. And yet, the light leaving that faint point in the southern sky, the light that will enter your eye tonight if you step outside and look up, left its source 4 years and 3 months ago. It departed before most of the conversations you remember having. It was already traveling towards you when events you can clearly recall were still in the future. It crossed an emptiness so vast that even at 186,000 miles per second, moving without pause, without friction, without anything to slow it down, the journey still consumed 4 years of time. That is how far away our nearest stellar neighbor is. And here is what most people, even those who know this fact, consistently fail to grasp. That distance, 4.24 light-years, 25 trillion miles, the closest any other star comes to our sun, is not a number that describes something far away in the way that Tokyo is far from London or the moon is far from Earth. It is a number that describes something so remote that every framework of distance human beings have ever developed becomes useless in its presence. Our fastest spacecraft, traveling at speeds that would circle Earth in minutes, would require longer than all of recorded human civilization to cover that distance. Our radio signals, traveling at the speed of light itself, take over 4 years to arrive. And yet, for reasons that say something profound about what we are, we want to go there. Not just to send a probe, not just to aim a telescope. We want to send people, living human beings, with hearts and memories and the full weight of everything they would be leaving behind. We want to send them across 25 trillion miles of vacuum and radiation and silence in a metal vessel, sustained by recycled air and artificial light, for a journey that would consume decades of their lives. This video is about what that would actually mean. Not the optimistic version, not the version where the engineering challenges are hand-waved away and the crew arrives healthy and triumphant at a lush, welcoming world. The real version, the version where every obstacle is examined, every cost is counted, every consequence is followed to its conclusion. Because the journey to Alpha Centauri is not simply difficult. It is not simply a matter of waiting for better technology or larger budgets. It is something categorically different from anything our species has ever attempted to test, not just of our engineering, but of our endurance, our psychology, our values, and our willingness to confront the full scale of what the universe actually is. By the time we are finished, you will understand exactly why this journey is terrifying, and you will understand just as clearly why we will attempt it anyway. If you find yourself drawn to explorations like this, journeys that take you to the edge of what we know, and ask you to look over, consider subscribing and leaving a like. It is a small gesture, but it genuinely determines whether this channel can keep making work like this. Your support matters more than you might think. Now, get comfortable. Turn down the lights if you like, because we are going to Alpha Centauri. Let's begin. The system we are traveling to is not a single star. This is the first thing worth understanding clearly. because the name Alpha Centauri suggests a singular destination, and the reality is considerably more complex. Alpha Centauri is a triple star system, 3 stars bound together by mutual gravity, moving through the galaxy as a unit. 2 of them, designated Alpha Centauri A and Alpha Centauri B, are stars broadly similar to our own Sun. Alpha Centauri A is slightly larger and brighter than the Sun, a warm yellow-white star that, if placed at the center of our solar system, would feel familiar. Alpha Centauri B is slightly smaller and cooler, tending toward orange. The two orbit each other in an elongated ellipse, their separation varying between roughly 11 and 36 astronomical units, where 1 astronomical unit is the distance from Earth to our Sun. At their closest approach, they are roughly as far apart as Saturn is from our Sun. At their most distant, they are farther apart than Neptune. These 2 stars have been locked in this gravitational dance for approximately the same length of time our own solar system has existed, 5 billion years, give or take. They have been out there, circling each other in the dark, since before the Earth had oceans. The third member of the system is Proxima Centauri. It is nothing like its companions. Where Alpha Centauri A and B are substantial, Sun-like stars, Proxima is a red dwarf, a small, dim, cool object containing only about 12% of the Sun's mass. It emits less than 1/5 of 1% of the Sun's luminosity. If you replaced our Sun with Proxima Centauri, the sky would be a deeper red, the light wan and muted, and you would need to be far closer to feel any warmth at all. Proxima orbits both of its larger companions at an enormous distance, roughly 13,000 astronomical units, so far away that it takes approximately 550,000 years to complete a single orbit around the central pair. Proxima Centauri is also the closest of the 3 to Earth, at 4.24 light-years, which is why it carries the name it does, Proxima, from the Latin for nearest. In 2016, a team of astronomers using the European Southern Observatory's instruments in Chile made an announcement that sent a current of excitement through the scientific community. They had detected a planet orbiting Proxima Centauri, a rocky world, roughly Earth-sized, completing 1 orbit every 11.2 days. They named it Proxima Centauri B. Early analysis suggested it orbited within what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planetary surface. For a brief, intoxicating moment, it seemed as though our nearest stellar neighbor might harbor something extraordinary, a world, perhaps a world with water, perhaps a world with more than that. We will return to what we now know about Proxima Centauri B, what it likely is, what it might be, and what anyone who actually arrived there would find. But first, we need to confront the distance itself, not as an abstraction, but as a physical reality that shapes every aspect of what a journey there would require. The Parker Solar Probe was launched by NASA in August of 2018. It is, by any measure, the fastest human-made object ever built. Its mission is to study the Sun at close range, and to achieve this, it uses the Sun's own gravity in a series of passes that bring it progressively closer to the solar surface. During these close approaches, the Sun's gravitational pull accelerates the probe to extraordinary velocities. At its peak speed, the Parker Solar Probe travels at approximately 430,000 miles per hour. This is not a number that registers intuitively. At that velocity, you could travel from the surface of Earth to the Moon in less than 35 minutes. You could circle the Earth's equator in under 4 minutes. In a single second, you cover roughly 120 miles. It is, by every standard of human engineering, blindingly fast. It is also nowhere near fast enough. If the Parker Solar Probe were pointed directly at Proxima Centauri, which it is not, and which would be physically impossible given its current trajectory, it would arrive in approximately 6,700 years, not decades, not centuries, 6,700 years. The entirety of recorded human history spans roughly 5,000 years. The first cities in Mesopotamia, the construction of the pyramids, the rise and fall of every empire you have ever studied, all of it fits inside a period shorter than the travel time of our fastest spacecraft to our nearest stellar neighbor. and that estimate assumes the probe could maintain its peak velocity, which it cannot. The Parker Solar Probe achieves its extraordinary speed by falling toward the Sun and using gravitational assistance. In the cold of interstellar space, far from any massive body capable of providing such assistance, the probe would gradually decelerate. The actual travel time would be considerably longer. This is the first wall, the first place where the human mind, accustomed to a world where technology reliably shrinks distances, runs directly into a limit that does not yield to cleverness or ambition. The stars are not far away in the way that continents are far away. They are not even far away in the way that planets are far away. They exist at a remove so complete that our current best technology, pushed to its absolute limits, cannot bridge the gap within any time frame that a human civilization could meaningfully sustain. To reach Alpha Centauri in a human lifetime in, say, 40 to 50 years, a spacecraft would need to travel at roughly 10% of the speed of light. That is approximately 67 million miles per hour, 150 times faster than the Parker Solar Probe at its peak, roughly 18,600 miles every second, continuously, for decades. Nothing we have ever built approaches this. Nothing currently under active development approaches this. The gap between where we are and where we need to be is not a gap that will be closed by refining existing technology. It requires something fundamentally different. So what are the options? What does physics actually permit? The first serious proposal for interstellar propulsion that moved beyond pure speculation was studied in the late 1950s under the name Project Orion. The concept was breathtaking in its audacity and disturbing in its details. You would accelerate a spacecraft by detonating nuclear bombs behind it. A massive plate, the pusher plate, would absorb each explosion, and a system of shock absorbers would transfer the impulse to the vehicle. Detonate enough bombs in rapid succession, and you could reach several percent of the speed of light. The physics worked. Computer simulations run by serious scientists at Los Alamos confirmed that the concept was viable. A spacecraft built on Orion principles could, in theory, reach Alpha Centauri in something between a century and a few centuries, depending on design parameters. But the concept was killed not by physics, but by reality. You would need thousands of nuclear weapons, small ones, but nuclear nonetheless. The radiation environment around the pusher plate during acceleration would be severe. The engineering challenges of building a structure that could survive thousands of sequential nuclear detonations were immense, and launching such a vehicle from Earth's surface would scatter radioactive fallout across the planet. The Partial Test Ban Treaty of 1963 effectively ended any realistic path forward for Orion. The idea exists today in textbooks and the imaginations of aerospace engineers, a monument to a road not taken. Fusion propulsion represents a more refined approach. The sun is powered by fusion, the process by which hydrogen nuclei are forced together under extreme temperature and pressure to form helium, releasing energy in the process. The energy yield per unit mass is roughly 10 million times greater than chemical combustion. If you could harness a controlled fusion reaction in a spacecraft engine, you could achieve exhaust velocities far beyond anything chemically possible and reach Alpha Centauri in decades rather than millennia. The problem is that controlled fusion has been tantalizingly close for 7 decades without quite arriving. Researchers have achieved fusion reactions in laboratories. The National Ignition Facility in California achieved fusion ignition net energy gain from a fusion reaction in December of 2022, a historic milestone. But the distance between a laboratory demonstration and a compact, reliable fusion engine capable of operating continuously for 40 years is vast. We do not yet know how to build one. We do not know if the materials science required is achievable. Optimistic projections suggest a practical fusion reactor for power generation might exist by mid-century. A fusion rocket suitable for interstellar travel is another order of magnitude beyond that. Antimatter propulsion would be, if achievable, the most powerful propulsion system physics permits. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass into energy. Einstein's equation tells us that even a small amount of mass, fully converted, yields an enormous amount of energy. A kilogram of antimatter, annihilating with a kilogram of ordinary matter, releases energy equivalent to roughly 43 megatons of TNT, comparable to the most powerful nuclear weapon ever detonated. The efficiency is unmatched, but the practical obstacles are staggering. Antimatter does not exist in nature on Earth in usable quantities. It must be manufactured in particle accelerators, and the process is extraordinarily inefficient. The total amount of antimatter ever produced by all of humanity's particle accelerators combined is less than 20 nanograms, 20 billionths of a gram. At current production rates, accumulating a single gram would take billions of years. The energy cost of production exceeds the energy that could be extracted from the resulting antimatter by a factor of billions. And storing it is nearly impossible. Any contact with ordinary matter causes immediate annihilation. Perfect magnetic containment would be required for decades. A single failure would be catastrophic. Antimatter propulsion is not engineering. It is currently closer to alchemy. Ion drives are real. We use them. NASA's Dawn mission used ion propulsion to orbit both the asteroid Vesta and the dwarf planet Ceres, becoming the first spacecraft to orbit two extraterrestrial bodies. Ion drives work by ionizing a propellant, typically xenon gas, and accelerating the ions using electric fields. The exhaust velocity is far higher than chemical rockets, making them extremely efficient. But the thrust is tiny, measured in millinewtons, roughly the force of a piece of paper resting on your palm. They are excellent for slow, patient missions within the solar system. For interstellar travel, they are inadequate by orders of magnitude. And then there is the solar sail. Light carries momentum. When photons strike a reflective surface, they transfer a tiny impulse. Build a sail large enough and light enough, and the cumulative pressure of sunlight could accelerate a spacecraft without any propellant at all. The Japanese spacecraft Arose demonstrated solar sail technology in 2010, becoming the first spacecraft to use solar radiation pressure for sustained propulsion. It worked, but sunlight is weak. At Earth's distance from the Sun, the radiation pressure is approximately 9 millionths of a Newton per square meter. To get meaningful acceleration, you need a sail measured in square kilometers, with an areal density of grams per square meter thinner than the thinnest material we can currently manufacture at scale, and strong enough to survive the stresses of acceleration without tearing. And the sun's light weakens as you move away from it. By the time you have passed the orbit of Mars, the acceleration has dropped to a fraction of what it was at Earth. The sail becomes useless long before it has generated the velocity an interstellar mission requires, unless you replace the sun with something more powerful. In 2016, the Breakthrough Starshot initiative, funded by physicist and entrepreneur Yuri Milner and backed by the late Stephen Hawking, announced a proposal that represented the most technically credible near-term approach interstellar travel yet conceived. The concept was elegant in outline. Build a ground-based laser array with a combined power output of roughly 100 gigawatts. Construct a fleet of tiny spacecraft, each one a gram-scale chip of electronics attached to a lightweight reflective sail a few meters across. Aim the laser at each sail in turn and accelerate it to 20% of the speed of light in a matter of minutes. At 20% of light speed, the journey to Proxima Centauri takes approximately 20 years. The concept is sound, the physics permits it, but the engineering challenges are extraordinary. A 100 gigawatt laser array, the output of roughly 100 large power plants, focused to a beam with the precision needed to track a tiny, rapidly accelerating sail, does not exist. The adaptive optics systems required to compensate for atmospheric distortion and maintain focus on a target moving away at thousands of kilometers per second do not exist. The materials capable of reflecting that concentrated beam without vaporizing have not been developed, and the spacecraft itself, being gram-scale, cannot carry humans, meaningful scientific instruments, or a transmitter powerful enough to send back high-resolution data across 4 light-years. Breakthrough Starshot is a probe mission, a first glimpse a photograph from a flyby that cannot slow down, cannot orbit, cannot land. It would scream past Proxima Centauri at 20% of light speed, spending perhaps a few hours in the system before disappearing into interstellar darkness forever. For human interstellar travel, the challenge remains unsolved. Every option either does not work, does not exist, or cannot be scaled to carry people. This is not pessimism, it is an honest account of where the physics and the engineering stand today. The wall is real, but walls in the history of our species have a tendency to eventually come down. So let us make an assumption, not a guaranteed one, not one we can put a date on, but a reasonable one given the trajectory of human technological development. Let us assume that sometime in the coming centuries, a propulsion system is developed that can accelerate a crewed spacecraft to 10% of the speed of light. Not 20%, not 50, 10, roughly 67 million miles per hour. At that speed, the journey to Proxima Centauri takes approximately 42 years. 42 years. Sit with that number for a moment. If you are 30 years old when the spacecraft departs, you will be 72 years old when it arrives. If the mission launches when your children are young, they will be middle-aged by the time you reach the destination. Every person you left behind will have aged by 4 decades. Some will be gone. The world you departed will be unrecognizable. And you older, changed in ways you cannot anticipate, carrying 42 years of a life lived in a metal vessel, will be standing at the edge of another star system, looking at a world no human being has ever seen up close. This is the scenario we need to examine. Not the launch, not the technology, not the abstract physics, the reality, the 42 years, what they would actually contain, because this is where the journey stops being an engineering problem and starts being a human one. 42 years at 10% of the speed of light. Before we can understand what that journey means for the people aboard, we need to understand what it means for the vessel itself. Because at 10% of the speed of light, the universe stops behaving the way it does in everyday experience. The rules change. Physics asserts itself in ways that are deeply counterintuitive and in some cases, deeply hostile. Let us begin with the most immediate problem, the one that would kill you before anything else. Space is not empty. This is one of those statements that sounds dramatic, but is, in fact, a precise physical description. The interstellar medium, the material that fills the space between stars, contains gas, primarily hydrogen and helium, at extraordinarily low densities. It contains dust grains, microscopic particles of silicate and carbon compounds, ranging in size from a few molecules to perhaps 1/10 of a millimeter across. It contains larger objects, grains of sand, pebbles, fragments of rock left over from ancient collisions, drifting in the dark without destination. At the speeds of conventional spacecraft tens of thousands of miles per hour, none of this presents a significant hazard. A grain of sand striking a spacecraft at 25,000 miles per hour carries the kinetic energy of a small bullet. Unpleasant, but manageable with adequate shielding, the hull of the International Space Station accumulates micrometeorite impacts continuously. It is designed to survive them. At 10% of the speed of light, the calculation changes completely. Kinetic energy scales with the square of velocity. Double your speed, and the kinetic energy quadruples. Increase your speed by a factor of 1,000, as we are doing when we compare conventional spacecraft to a 10% light speed vehicle, and the kinetic energy increases by a factor of 1 million. A grain of sand massing 1 milligram, striking a spacecraft traveling at 10% of light speed, delivers kinetic energy, roughly equivalent to several kilograms of TNT. Not a scratch on the hull, not a small breach, an explosion, a gram-scale pebble, the kind you might absent-mindedly kick along a sidewalk, would strike with energy comparable to a nuclear weapon. A rock the size of your fist would be an extinction-level event for the spacecraft and everyone aboard. There is no way to clear the path. There is no way to know where every grain of dust and sand in 4.24 light-years of interstellar space is located. There is no way to stop and wait for the debris to clear. At 10% of light speed, you are covering roughly 18,600 miles every second. An object detected at a distance of 100,000 miles, which is itself an extraordinarily optimistic detection range for a grain of sand in interstellar space, would reach you in less than 6 seconds. There is no time to maneuver. The only viable solution is a shield. A massive, dense shield positioned at the front of the spacecraft, designed to absorb impacts before they reach the crew sections. The material would need to be both strong enough to survive the impacts and light enough not to make the spacecraft impossibly heavy to accelerate. Beryllium, tungsten carbide, and advanced composite materials have been proposed. Some designs suggest a layered approach, a sacrificial outer layer that vaporizes on impact, with the expanding plasma from the vaporization spreading the remaining energy across a larger area before it reaches structural elements. But every gram of shielding is a gram the propulsion system must accelerate across 4.24 light-years. And more shielding means more mass, which means more fuel, which means more mass still. This is the tyranny of the rocket equation, which we will return to in a moment. For now, simply note that the shield required to protect a crewed spacecraft at 10% of light speed would be substantial, heavy, and still not guaranteed. Interstellar travel, at the speeds required to reach Alpha Centauri in a human lifetime, means accepting that you are flying through a minefield you cannot see, protected by a wall you hope is thick enough, at a speed that leaves you almost no time to react to anything. That is the first hazard. The second is invisible, and in some ways it is worse. Cosmic rays are not rays in any conventional sense. The name is a historical accident, coined in the early 20th century, before their true nature was understood. They are in fact particles, primarily protons and atomic nuclei, accelerated to extraordinary energies by the most violent events in the universe. Supernova explosions, pulsar winds, the accretion disks of black holes. These particles travel through the galaxy at velocities approaching the speed of light, carrying energies that can exceed anything producible by any particle accelerator on Earth. On Earth's surface, you are protected from this constant bombardment by two overlapping shields. The first is the planet's magnetic field, which deflects charged particles away from the surface. The second is the atmosphere, equivalent to roughly 10 meters of water in terms of radiation shielding, which absorbs the particles that do make it through. Together, they reduce your annual radiation dose from cosmic rays to a negligible level, a fraction of what you receive from medical X-rays and naturally occurring radioactive materials in the ground beneath you. Remove both shields, and the situation changes dramatically. Astronauts aboard the International Space Station, operating in low Earth orbit, where the planet's magnetic field still provides partial protection, receive radiation doses roughly equivalent to several hundred times what you receive on the surface. On a mission to Mars, crossing the inner solar system, and spending months on a planet with no global magnetic field and a thin atmosphere, a crew would receive a cumulative dose that NASA estimates at several hundred millisieverts, approaching the career limit for astronauts, all in a single mission. Between the stars, there is no planetary magnetic field, there is no atmosphere, there is no star close enough to provide the solar wind that partially moderates the cosmic ray environment in the inner solar system. The spacecraft itself provides some shielding, but stopping high-energy cosmic rays requires enormous amounts of material. The most energetic cosmic ray particles can punch through meters of lead. No practical spacecraft hull provides adequate protection against them. Over 42 years of continuous exposure, the cumulative radiation dose received by the crew would be far beyond any threshold considered safe for human health. Cancer rates would be dramatically elevated. Cataracts would be nearly universal. DNA damage would accumulate in every cell of every body, increasing the risk of heritable mutations. Some crew members would develop radiation sickness. Some would die of radiation-induced cancers before the journey ended. This is not speculation. It is a straightforward extrapolation of known physics and known biology. The radiation environment of interstellar space, experienced for 4 decades, would leave marks on every person who survived it. Proposed mitigations exist. A magnetic shield, a superconducting loop generating a powerful magnetic field around the spacecraft, mimicking Earth's magnetosphere, could deflect some of the incoming charged particles. Such a system has been studied seriously, most notably in the European Space Agency's SR2S project. But generating and maintaining a magnetic field strong enough to provide meaningful protection requires substantial power, complex superconducting systems that must operate flawlessly for decades, and adds mass to a spacecraft already struggling against the rocket equation. And magnetic fields deflect only charged particles. Neutral particles and high-energy gamma rays pass straight through. Radiation, micrometeorite impacts, two hazards that exist before the journey even begins in earnest, before the engines fail, before the food runs out, before the psychological weight of 42 years in a closed environment begins to press down on the crew. These hazards are simply the ambient conditions of interstellar space. This is what the universe is like between the stars. And still, we have not yet discussed the propulsion problem in its full depth. The rocket equation was derived in the late 19th century by a Russian schoolteacher and self-taught mathematician named Konstantin Tsiolkovsky, working in a small town in provincial Russia. Largely unknown to the scientific establishment of his time, Tsiolkovsky developed the mathematical framework that describes how rockets work. His equation, elegant and merciless, relates the change in velocity a rocket can achieve to the ratio of its initial mass, including fuel, to its final mass after the fuel is expended. The equation has a consequence that feels almost designed to frustrate human ambition. To go faster, you need more fuel, but fuel has mass, and accelerating that mass requires more fuel still. The relationship is not linear, it is exponential. To double your final velocity, you do not double your fuel requirements, you square them. To achieve 10 times the velocity, you need exponentially more than 10 times the fuel. For a journey to Alpha Centauri at 10% of light speed, the rocket equation is essentially a wall. A spacecraft using the best chemical propellants available would need a fuel-to-payload ratio that no engineer can make work. The fuel required would outweigh the spacecraft it was meant to propel by factors that simply cannot be built. You would need a fuel tank the size of a small moon to move a vehicle the size of a house. This is why nuclear propulsion is the minimum viable option for crewed interstellar travel. The energy density of nuclear reactions, the amount of energy released per kilogram of fuel, is millions of times greater than chemical combustion. Nuclear fuel carries more energy per unit mass than anything chemically possible, which means the fuel-to-payload ratio becomes, if not comfortable, at least theoretically achievable. But there is a further complication, one that is easy to overlook when thinking about the journey in the abstract. Getting to 10% of light speed is only half the problem. If a spacecraft accelerates to 10% of light speed and cannot slow down at the destination, the entire mission becomes a flyby. The crew would arrive at Proxima Centauri at 67 million miles per hour, spend perhaps a few hours in the system, not even enough time to fully image the planet, and then continue into the darkness beyond, with no way to stop, no way to turn around, and no destination ahead of them. They would travel until life support failed, decades or centuries from now, alone in the space between stars that grow no closer. To enter orbit around Proxima Centauri b, the spacecraft must decelerate, and the rocket equation does not care whether you are accelerating or decelerating. It demands the same fuel mass for the same change in velocity, in either direction. This means a ship designed to arrive in orbit needs roughly twice the fuel of one designed only to get there, or it needs an entirely different approach to deceleration. Several proposals have been studied. A magnetic sail could use the stellar wind of Proxima Centauri charged particles streaming outward from the star to create drag that slows the spacecraft as it approaches. The physics is sound, but Proxima Centauri is a red dwarf with an irregular, relatively weak stellar wind compared to our Sun, and the deceleration forces achievable are modest. Slowing from 10% of light speed to orbital velocity using a magnetic sail around Proxima Centauri would take years, possibly decades, adding substantially to the already immense journey time. A light sail could be deployed and oriented to catch photons from Proxima Centauri as the spacecraft approaches, using the star's own light as a brake. Again, physically possible, but red dwarfs are dim. Proxima emits less than 1/500th of the Sun's luminosity. The braking force would be very weak. The deceleration distance, the space required to bleed off the velocity, would be measured in light months. Or the spacecraft could carry extra fuel, enough to both accelerate at the start and decelerate at the end. But this compounds the rocket equation's demands exponentially. The fuel mass required for a complete mission, full acceleration and full deceleration, is not twice the fuel mass of an acceleration-only mission. It is far more than twice. The numbers escalate rapidly toward the physically unrealizable. Every path to Alpha Centauri that involves a crewed vessel arriving safely and entering orbit carries within it this deep tension between what physics demands and what any spacecraft can physically carry. There is no clean solution. There is only engineering, creativity, and the slow accumulation of knowledge that might, over centuries, find a path through. Imagine, for a moment, a scale model. Shrink the Sun to the size of a grapefruit. At that scale, Earth is a small seed, about 3/4 of an inch in diameter, orbiting roughly 26 feet away. The outermost planets of our solar system, Neptune, Uranus, are several hundred feet out. Voyager 1, the farthest human-made object, launched in 1977, is currently about 140 feet from the grapefruit in this model, still technically within the outermost boundaries of the solar system's influence. In this same scale model, Alpha Centauri is approximately 1,400 miles away, 1,400 miles. In a model where the entire solar system fits within a few hundred feet, our nearest stellar neighbor is 1,400 miles distant, New York to Denver, London to Moscow. If Voyager 1 were traveling toward Alpha Centauri at its current speed, which it is not, it would cover, in this scale model, roughly 100 feet per year. It has been traveling for nearly 50 years. It has covered, at this scale, less than the length of a city block. The nearest star is 1,400 miles away, and our fastest spacecraft has moved less than the length of a block in 50 years. This is the physical reality we are asking engineers to overcome. This is the wall the rocket equation builds between us and the stars. And yet the wall is not infinite. It is merely very, very high. The breakthrough Starshot proposal, for all its limitations as a probe concept, demonstrates something important. Laser propulsion, in principle, sidesteps the rocket equation entirely. If the energy source stays at home, the laser array on Earth, and only the sail and payload are accelerated, then the payload carries no fuel at all. The rocket equation does not apply. You are limited instead by the power of your laser, the reflectivity of your sail, and the engineering challenges of building both at the required scale. A crude version of this concept is not currently imaginable. The power required to accelerate a vessel massing hundreds of tons to 10% of light speed using a laser would be measured in petawatts, millions of gigawatts sustained for years. The waste heat alone would require radiating systems of planetary scale. The sail would need to be hundreds of kilometers across. The technological gap between where we are and where this concept requires us to be is so vast that it cannot be measured in decades. It is measured in centuries, possibly more. But here is the thing about centuries. We have been a technological civilization for approximately 250 years. We went from the first powered flight to landing on the moon in 66 years. We went from discovering the structure of DNA to routinely editing genomes in less than 70. The pace of technological change is not constant, it accelerates, and the universe does not have a deadline. If humanity survives, if we do not destroy ourselves, if we navigate the coming centuries without catastrophe, then the technologies required for interstellar travel will eventually exist. Not because we willed them into being, but because the underlying physics permits them, and because the pattern of human inquiry tends, over long timescales, to find what physics permits. The question of Alpha Centauri is not whether we will eventually have the technology to go. The physics says we will, given enough time. The question is what it will cost in resources, in time, in human lives, and whether those who go will understand, truly understand, what they are accepting. Because the technology is only the beginning of the problem. It is, in many ways, the simplest part. A rocket engine, once built, either works or it does not. A radiation shield either blocks particles or it does not. These are engineering problems, and engineering problems, in principle, have solutions. You iterate, you test, you fail, you improve, and eventually you succeed. The harder problems are the ones that do not yield to iteration and testing, the ones that live not in the machinery, but in the people, the ones that accumulate slowly over 42 years of confinement, growing heavier with each passing month until they either break the mission or forge it into something extraordinary. Those problems are what the next part of this journey examines. But before we go there, consider one final image. You are standing in a field at night. The sky is clear. You have driven far from city lights, and the Milky Way is visible overhead, a faint, diffuse band of light crossing the sky from horizon to horizon. You know, intellectually, that each point of light in that band is a star. You know that each star is the size of our sun or larger. You know that the distances between them are measured in light years. And then you find the faint point of light that is Alpha Centauri, visible only from the southern hemisphere, in the constellation Centaurus, so unremarkable that most people who look directly at it have no idea what they are seeing. The light entering your eye right now left that star 4 years and 3 months ago. It traveled at 186,000 miles per second without pause. It crossed 25 trillion miles of emptiness and radiation and silence to reach you. And when it touches your eye in this field, on this quiet night, it completes a journey so vast that no human framework of scale can properly contain it. Now imagine going there, not the light, you, 42 years in a vessel. Everything you know receding behind you until it becomes a point indistinguishable from the darkness. Every person you love, aging without you. The universe growing stranger and more hostile with every passing year. Imagine it fully, hold the weight of it, and then ask yourself whether you would still go. Some of you would say yes, immediately, without hesitation. Something in you already knows the answer. That instinct that pull toward the unknown regardless of the cost is precisely what we need to examine next. The vessel that carries human beings to Alpha Centauri cannot be thought of as a spacecraft in any conventional sense of the word. A spacecraft, as we currently understand the term, is a machine. It is built for a mission. It carries its crew for weeks or months, sustains them through the specific challenges of that mission, and returns them to Earth. The International Space Station, the largest and most complex structure humanity has ever placed in orbit, is, by this definition, a spacecraft. It houses a rotating crew of 6, supports them for missions of 6 months to a year, and depends on regular resupply missions from Earth for food, water, spare parts, and the psychological lifeline of knowing that home is only a few hundred miles below. Remove the resupply missions, remove the proximity to Earth, remove the possibility of return, extend the mission duration from 6 months to 42 years. What you have is no longer a spacecraft. It is a world, a small world, a world measured in corridors and chambers rather than continents and oceans. A world where every cubic meter has been accounted for, every system has been designed and redundantly backed up, every resource flows in a closed loop from which nothing can escape because nothing can be replaced. A world where the population is fixed or nearly fixed, and where the death of any individual represents an irreplaceable loss of knowledge, skill, and labor. Building this world is the engineering challenge that dwarfs all others, not the propulsion, which is at least a problem with a single variable velocity, not the radiation shielding, which is at least a problem with a known enemy. The vessel itself is a problem with 10,000 variables, all of them interconnected, all of them critical, any one of which can cascade into catastrophic failure if it is not solved correctly. Let us build it, piece by piece, and examine what each piece actually requires. The first and most fundamental problem is gravity. The human body was designed, if we can use that word loosely, meaning shaped by billions of years of evolution, to function in a gravitational field of approximately 9.8 meters per second squared. Every system in the body, from the architecture of bone to the behavior of the cardiovascular system to the mechanics of the inner ear, assumes this constant downward pull. Remove it, and the body begins, immediately and systematically, to adapt to its absence. This adaptation is not benign. Bone density decreases. In the absence of gravitational load, the body's bone remodeling system concludes that the skeleton is stronger than it needs to be and begins reducing it. Astronauts on the International Space Station lose approximately 1 to 2% of bone density per month in the most weight-bearing regions of the skeleton, the hips, the spine, the femur. On a 6-month mission, this loss is substantial, but largely recoverable, with rehabilitation on return to Earth. Over 42 years, it would be catastrophic. Bones that have lost decades of density do not recover. They become fragile, prone to fracture, structurally compromised in ways that cannot be reversed. Muscle mass atrophies at a similar rate. The muscles responsible for maintaining posture, for supporting the spine, for enabling the simple act of standing upright, receive no signals in weightlessness. The body, ruthlessly efficient in its resource allocation, begins to dismantle them. Astronauts on long-duration missions exercise 2 hours per day specifically to slow this process. Even so, they return to Earth unable to walk normally, requiring weeks of rehabilitation to recover basic motor function. The cardiovascular system restructures itself. In weightlessness, fluid that normally pools in the lower body redistributes upward toward the head and chest. The heart, sensing a higher blood volume in the upper body, responds by reducing its overall output. Over time, it actually shrinks. The blood vessels adapt to lower pressures, return to a gravitational environment, and the cardiovascular system is suddenly inadequate. Blood pressure drops. The astronaut feels faint. The heart struggles to maintain circulation. Vision changes. Fluid pressure in the skull increases in microgravity, pressing on the optic nerve and flattening the back of the eyeball. A significant fraction of astronauts on long-duration missions return to Earth with measurably degraded vision, some of it permanent. The syndrome has a name, spaceflight-associated neuro-ocular syndrome, and it is not fully understood. We do not know why some astronauts are more affected than others. We do not know if the effects worsen with longer exposure. The immune system weakens. Latent viruses, herpes simplex, varicella zoster, the virus that causes chickenpox, reactivate in astronauts in space, suggesting that immune suppression is a reliable consequence of spaceflight. The mechanisms are not fully understood, but the pattern is consistent. All of this, from missions lasting 6 months to a year, in a low Earth orbit environment that at least provides some of the protection of Earth's magnetic field. 42 years. On a 42-year mission with no gravity, every member of the crew would arrive at Alpha Centauri. If they arrived with skeletons so compromised they could barely stand, cardiovascular systems incapable of functioning in a gravitational environment, muscles atrophied beyond functional recovery, and vision degraded to an unknown degree, they would be, in the most literal physical sense, unable to perform the mission they had traveled 4 light-years to execute. Artificial gravity is not optional. It is the absolute prerequisite for human interstellar travel. The only practical method available with known physics is rotation. A spinning structure experiences centrifugal force, technically a pseudo-force, an artifact of the rotating reference frame that pushes everything toward the outer edge. Stand on the inner surface of a rotating cylinder, and you feel a force pressing you toward the hull that mimics, functionally, gravity. Spin it at the right rate, and that force is indistinguishable from Earth's gravity in its biological effects. The mathematics of this are straightforward. The centripetal acceleration felt on the inner surface of a rotating cylinder is equal to the radius of the cylinder multiplied by the square of its angular velocity. To achieve 1 Earth gravity, the same pull you feel right now in a cylinder with a radius of 50 meters, the cylinder must rotate approximately 4 times per minute. In a cylinder with a radius of 100 meters, it must rotate approximately 3 times per minute. These numbers seem manageable, but they come with a complication that cannot be engineered away. When you move in a rotating reference frame, you experience what is called the Coriolis effect. It is the same phenomenon that causes weather systems to rotate the deflection of moving objects relative to the surface of a rotating body. In a spacecraft, The Coriolis effect manifests as a strange sideways force whenever you move. If you walk in the direction of rotation, you feel heavier. Walk against the rotation, and you feel lighter. Raise your arm, and it feels as though it is being pulled sideways. Turn your head quickly, and your inner ear sends signals that do not match what your eyes are seeing, causing disorientation and, in some people, severe nausea. The severity of the Coriolis effect depends on the radius of rotation and the rotation rate. Smaller radius, higher rotation rate required for the same gravity, stronger Coriolis effects. Larger radius, lower rotation rate, weaker Coriolis effects. Studies of human tolerance suggest that rotation rates above about 2 revolutions per minute produce noticeable and unpleasant Coriolis effects for most people. Below 2 revolutions per minute, most people adapt within a few days. To stay below 2 revolutions per minute while achieving 1 Earth gravity requires a rotation radius of approximately 225 meters. The rotating section of the spacecraft must be nearly 1/4 of a kilometer in diameter. For comparison, the International Space Station, the largest object humanity has ever assembled in space, is approximately 109 meters across at its widest point, from solar array tip to solar array tip. The pressurized volume where crew live and work is considerably smaller. An interstellar vessel with a rotating habitat section 225 meters in radius is an engineering project of extraordinary scale. It must be constructed either on Earth and launched, or assembled in orbit from components. It must be structurally capable of maintaining its rotation for 42 years while subjected to the stresses of acceleration, deceleration, and the constant centrifugal force on its own structure. Its bearings, if it uses bearings to isolate the rotating section from the non-rotating propulsion and shield assemblies, must operate without maintenance for 4 decades. And it must be moved, all of it, at 10% of the speed of light. Every gram of structure in that rotating habitat section must be accelerated to 67 million miles per hour, and then, at the journey's end, decelerated back to orbital velocity. The rocket equation applies to every kilogram of that rotating ring, every meter of corridor, every wall panel, every piece of equipment. The fuel required to move a structure of this size across 4.24 light-years would be measured in the mass of small asteroids. This is before we have added a single human being, a single kilogram of food, a single liter of water. Let us talk about power. A crewed interstellar vessel requires power in quantities that have no precedent in the history of human spaceflight. Life support systems, the machinery that maintains breathable air, drinkable water, stable temperatures, and adequate pressure, require continuous electrical power. The lighting that prevents the crew from descending into psychological darkness requires power. The computers that monitor 10,000 systems simultaneously require power. The medical equipment requires power. The communication systems require power. The artificial gravity's rotation mechanism requires power. The propulsion system requires power, orders of magnitude beyond all of these combined. Solar panels will not work. At the distance of Mars, sunlight is already roughly 40% the intensity it is at Earth. At Jupiter, it is less than 4%. By the time a spacecraft is even a fraction of a light year from the Sun, the star has become just another point of light in the sky, providing negligible energy. Solar power is not a viable option for interstellar travel. Nuclear fission is the only realistic power source available with known technology. A fission reactor converts the energy released by splitting heavy atomic nuclei uranium or plutonium into heat, which is used to generate electricity. Fission reactors are compact, reliable, and energy-dense. They have powered submarines continuously for decades. NASA's Killer Power project has developed a small fission reactor designed for space applications capable of producing 10 kilowatts of electrical power from a system massing less than a metric ton. But an interstellar vessel needs not 10 kilowatts, but megawatts, possibly hundreds of megawatts. Multiple reactors would be required, both to provide sufficient power and to ensure redundancy, because a single power failure on an interstellar mission is not an inconvenience. It is a death sentence. The life support system does not function without power. The heating systems that prevent the vessel from cooling to the ambient temperature of interstellar space, approximately minus 270 degrees Celsius, 3 degrees above absolute zero, do not function without power. The crew would be dead within hours. Multiple redundant reactors, each capable of sustaining the critical systems independently, are the minimum viable approach. Each reactor requires fuel, uranium or plutonium, carried from Earth at launch, sufficient for 42 years of continuous operation. Each reactor produces waste heat that must be eliminated. In space, waste heat cannot be convected or conducted away. There is no air, no water, no medium for those transfer mechanisms. It must be radiated away as infrared light through large panels called radiators, positioned to avoid interfering with the vessel's other systems. Large radiators, exposed to the interstellar environment, required to function for 42 years without significant degradation. Every square meter of radiator is a surface that can be struck by micrometeorites. Every connection between the reactor and the radiator panels is a potential failure point. Every kilogram of radiator mass must be accelerated to 10% of light speed and decelerated again at the destination. Power is not a solved problem. It is a deep, compounding problem that grows more complicated with every system it must support. Now we reach what is perhaps the most intimate engineering challenge of the entire mission: the air, the water, and the food. You breathe approximately 550 liters of air per day. Of that, roughly 200 liters is the oxygen you consume. You exhale carbon dioxide. On Earth, this presents no problem. The atmosphere is vast. Plant life continuously replenishes oxygen, and the carbon dioxide you exhale disperses harmlessly into a volume of gas that is effectively infinite. On an interstellar spacecraft, the atmosphere is a closed system. Every molecule of oxygen that goes into a crew member's lungs must eventually come back out. Every molecule of carbon dioxide exhaled must be captured before it reaches toxic concentrations and converted back into oxygen. The system cannot lose gas. Any loss accumulates over 42 years into a significant deficit that cannot be replenished. The International Space Station manages this through a combination of chemical and mechanical systems. Carbon dioxide is captured by adsorbent beds and either vented to space, a luxury an interstellar mission cannot afford, or processed through the Sabatier reaction, which combines carbon dioxide with hydrogen to produce water and methane. The water can be electrolyzed back into oxygen and hydrogen, closing the loop. The methane is currently vented on the ISS, but on an interstellar mission, it would need to be processed further to recover the carbon for other uses. Plants complicate and enrich this picture. Photosynthesis is the most efficient biological mechanism for converting carbon dioxide back into oxygen while simultaneously producing food. An interstellar vessel with extensive hydroponic growing areas would simultaneously manage its atmospheric chemistry and feed its crew. The two systems reinforce each other, but growing enough food for a crew of 100, a crew size we will return to when we discuss the human aspects of the journey, requires substantial area and substantial light. Crops need roughly 200 to 400 watts of light per square meter during their growing period. For a meaningful food production system, you need hundreds or thousands of square meters of growing area. The lighting alone would require megawatts of power, and the growing systems must be protected from contamination. A fungal or bacterial outbreak that destroys a crop in a sealed system cannot simply be replaced with a trip to the market. Water, similarly, must be recovered and recycled with near-perfect efficiency. The International Space Station already achieves approximately 93% water recovery, recycling urine, wash water, and atmospheric moisture back into drinking water. On an interstellar mission, that number must approach 100%. Any loss, every drop of water that is not recovered, every molecule that ends up chemically bound in a form that cannot be retrieved, represents a permanent reduction in the mission's water supply. Over 42 years, even a loss of 0.1% per year compounds into a meaningful deficit. The crew would need to be extraordinarily disciplined about water use. Every hygiene practice, every cooking method, every industrial process aboard the vessel would need to be designed with water recovery as a primary constraint. This is not a matter of conservation in the casual sense. It is a matter of survival. Think of it this way. Take a glass of water. Drink it. Your body absorbs some of it, uses it in metabolic processes, and excretes the rest as urine, sweat, and exhaled moisture. On an interstellar mission, every molecule of that water is tracked, recovered, purified, and returned to the drinking supply. The water you drink today was, last week, someone else's urine. This is not a problem to be squeamish about. It is a physical necessity. It is, in fact, what the water cycle on Earth does continuously at planetary scale. The interstellar mission simply does it at the scale of a single vessel, with no margin for error. Food cannot be fully recycled in the same sense. The calories consumed by the crew must be continuously produced, not recovered. This is why agriculture is essential. The crew must grow enough calories to sustain themselves indefinitely. A person requires roughly 2,000 to 2,500 calories per day. A crew of 100 requires approximately 200,000 to 250,000 calories per day, every day, for 42 years. This is not an amount that can be carried from Earth. It must be produced aboard the vessel. Wheat, rice, potatoes, soybeans, and leafy vegetables are among the most calorie-efficient crops under artificial lighting. A well-designed hydroponic system can produce more calories per square meter than traditional soil agriculture because every variable light, water, nutrients, temperature can be precisely controlled, but the system requires continuous management. Nutrient solutions must be maintained at correct concentrations. pH must be monitored. Pests and pathogens must be controlled without pesticides that would contaminate the crew's food and atmosphere. When something goes wrong, and over 42 years, many things will go wrong, it must be diagnosed and corrected before the crop fails. A crop failure in the early years of the mission, before reserves have been established, could be catastrophic. Emergency protocols would need to exist. Seed banks, preserved against contamination and radiation damage, would need to be maintained throughout the journey. The crew would need individuals with deep expertise in agriculture, plant pathology, and soil science. Or rather, hydroponic science. There is no soil. There is only the nutrient solution, the light, and the seed. Medical care on an interstellar vessel operates under a constraint that has no parallel in any other context humans have ever inhabited. There is no evacuation, there is no transfer to a higher level of care. There is no calling for help that will arrive before the patient has died, or recovered, or died again. Everything that can happen to a human body, every illness, every injury, every age-related decline must be manageable with the resources aboard the vessel. Appendicitis, heart attacks, strokes, broken bones, cancer, kidney failure, psychiatric emergencies, childbirth complications, surgical emergencies of every kind. The medical bay of an interstellar vessel must be, in capability, a small hospital staffed by physicians with the broadest possible range of expertise, equipped with the most compact and durable versions of diagnostic and treatment technology available. Medications degrade. This is an unforgiving chemical reality. Many pharmaceutical compounds break down over time, losing potency, sometimes developing toxic breakdown products. A medication dispensed in year 1 of the mission may have a very different effect in year 30. The vessel would need either an extraordinary stockpile of medications, all of which must be mass accelerated across 4.24 light years, or the capability to synthesize medications on demand from basic chemical precursors. Both approaches have been studied. Neither is simple. Both require expertise, equipment, and continuous power. And there is aging. The crew that departs Earth will be, at arrival, 42 years older than they were at launch. A crew selected at peak physical and cognitive fitness, likely in their late 20s to mid-30s, will arrive at Alpha Centauri in their 70s. The full spectrum of age-related medical conditions will have manifested over the course of the journey. The physicians treating these conditions will themselves be aging, their own reflexes and cognitive capacity gradually diminishing. The situation is not impossible. Elderly physicians practice medicine effectively on Earth. But the compounding of limited resources, limited expertise, limited equipment, and an aging population in an isolated environment creates a fragility that has no earthly equivalent. Some crew members will die during the journey. This is a statistical certainty on a 42-year mission. Disease, accident, the slow failures of aging mortality cannot be entirely prevented. The vessel must have protocols for handling death. The crew must have the psychological and cultural resources to grieve, to continue, to find meaning despite loss. The physical remains must be managed burial in space, if it means anything, or some form of storage, or a ceremony that acknowledges the reality without consuming resources needed by the living. Death is part of the mission. It must be planned for, not as a failure, but as an inevitability. Consider the weight of all of this, not metaphorically, literally. The weight of shielding against micrometeorite impacts, the weight of radiation shielding, the weight of the rotating habitat section, the weight of nuclear reactors and their radiators, the weight of water recycling systems and atmospheric processors, the weight of hydroponic growing areas and their lighting systems, the weight of a medical facility capable of handling 42 years of human health needs, the weight of spare parts, replacement components, tools, raw materials for manufacturing. A realistic estimate of the total mass of an interstellar vessel capable of carrying 100 people to Alpha Centauri in 42 years and safely delivering them into orbit runs into the hundreds of thousands of metric tons. Some estimates go higher. The Saturn V rocket, the most powerful launch vehicle humanity has ever built, the machine that sent 12 men to the moon, could lift approximately 130 metric tons to low Earth orbit. To assemble a vessel of the mass required for an interstellar mission, you would need thousands of Saturn V launches, or equivalents, just to get the material into orbit. Then, you would need to assemble it, over years or decades, in the hostile environment of space. And then you would need to move it. The fuel required to accelerate hundreds of thousands of metric tons to 10% of the speed of light is a number that strains the imagination. It would need to be gathered, refined, and loaded, a logistical operation that might require the industrial capacity of an entire civilization, sustained over decades. This is not a project for a nation. It is not a project for a generation. It is a project for a species, undertaken over timescales measured in centuries, driven by a motivation that transcends any individual life or any short-term calculation of benefit. And still, given all of this, the mass, the power, the engineering complexity, the 42-year duration, the radiation, the micrometeorites, the closed-loop life support, the medical challenges, the aging crew, the vessel is only the container. It provides the physical conditions necessary for survival. It does not address the deeper question: can human beings survive inside it? Not physically. Physically, with adequate engineering, survival is achievable. The question is whether they can survive in every other sense of the word, whether 42 years in a closed environment, separated from Earth by a distance, light itself takes 4 years to cross, surrounded by the same walls and the same faces and the same recycled air, day after day and year after year, can be endured without breaking the minds of the people it contains. Because a vessel, no matter how perfectly engineered, is nothing without the humans inside it. And humans, as it turns out, are far more fragile than any metal hull. That fragility is where we go next. There is a research station on the Antarctic plateau called Concordia. It sits at an altitude of 3,233 meters on a featureless expanse of ice that extends to every horizon without interruption. During the winter months, from February to November, it is completely inaccessible. No aircraft can land, no supply ship can reach it. The small team of researchers stationed there, typically between 12 and 16 people, are entirely cut off from the rest of humanity for approximately 9 months. The temperature outside can fall to -80 degrees Celsius. The sun disappears entirely for 4 months. The air is thin enough that newcomers spend weeks adjusting before they can work effectively. The horizon is perfectly flat in every direction. There is nothing to see that is not ice, sky, or the station itself. The European Space Agency uses Concordia as an analog for long-duration spaceflight. They send a medical researcher on every winter-over mission specifically to study what happens to human beings under these conditions. What they have documented consistently across multiple teams and multiple years is a pattern so reliable it has been given a clinical name. They call it the third quarter phenomenon. In the first months of isolation, the team functions well. Motivation is high. The novelty of the environment sustains engagement. People are cooperative, enthusiastic, focused on their work. There is a quality of shared adventure that binds the group together. Then, somewhere around the midpoint of the isolation, and particularly in the period from roughly halfway to 3/4 of the way through, something changes. Performance degrades. Cognitive speed slows measurably. Reaction times increase. Errors become more frequent. Mood drops. Interpersonal friction rises. Sleep disturbances become common. People become irritable over things that, in the outside world, would be trivial. A particular laugh. The way someone sets a cup down too loudly. The same story told for the fourth time. These are not weak people. They are scientists and engineers selected for psychological resilience, trained extensively for the mission, motivated by genuine interest in their work. And still, the isolation erodes them, slowly, persistently, in ways they often cannot fully perceive as they are happening. Concordia is 9 months, a crew of 12 to 16. With the knowledge that the isolation will end, that an aircraft will eventually land, that home is reachable. Now, remove the ending, remove the aircraft, remove the home. 42 years, perhaps 100 people, no return. The study of isolated and confined environments, what researchers call ice environments, has produced a body of literature that is, at its core, a record of human fragility under conditions the species was not designed to inhabit. Submarines, Antarctic stations, simulated Mars missions like the high seas studies in Hawaii, where crews of 6 spent up to 1 year in a dome on a volcanic slope, leaving only in spacesuits, with all communication to the outside world, subject to a 20-minute delay to simulate the communication lag of a Mars mission. Across all of these studies, certain patterns emerge with enough consistency to be treated as near certainties for any long-duration isolated mission. Cognitive performance degrades, not catastrophically, not in ways that make people non-functional, but measurably and progressively. Processing speed, working memory, executive function, the mental tools needed to diagnose a system failure, to perform surgery, and to navigate a complex engineering problem, all of them diminish in isolation. The reasons are not entirely understood. Sleep disruption contributes. Chronic low-level stress contributes. The monotony of unchanging environments may play a role. The brain, denied the constant flow of novel sensory input it evolved to process, may in some sense begin to disengage. For an interstellar mission, this degradation is a direct safety concern. The crew are not passengers, they are operators. Every critical system aboard the vessel requires human oversight, human diagnosis, human intervention when something goes wrong. A crew whose cognitive performance has degraded significantly over decades of isolation is a crew less capable of solving the problems that will inevitably arise. The vessel designed to keep them alive depends on their ability to think clearly. The isolation that is an unavoidable consequence of the mission undermines exactly that ability. Interpersonal conflict is universal in ice environments. Without exception, in every study of long-duration isolated teams, conflict emerges. The specific triggers vary: a perceived unfairness in work assignments, a personality clash that was manageable in normal life but becomes unbearable in confinement, a romantic entanglement that ends badly with no possibility of distance between the people involved. The content of the conflict matters less than its inevitability. Put any group of human beings in a confined space for long enough, and conflict will arise. On a mission lasting 9 months or a year, these conflicts are managed. People endure. They count the days. They remind themselves that it will end. The knowledge of an ending is itself a form of psychological anchor, something to hold on to when the friction becomes intense, a promise that relief is coming. On a 42-year mission, There is no ending to count toward, there is only more of the same. The corridor you are walking down today is the corridor you will walk down in 20 years and in 35 years. The face that is irritating you this morning is the face you will see at breakfast tomorrow and at breakfast in a decade. There is no escape, there is no relief, there is only endurance, and the slow work of making peace with a situation that will not change. Some people are capable of this. Psychologists studying Antarctic winter overs have identified a constellation of traits that predict successful adaptation to long-term isolation: high tolerance for ambiguity, strong intrinsic motivation, the ability to find meaning in routine, emotional stability under chronic stress, and critically the capacity to maintain positive relationships with others even in the absence of personal space and privacy. These traits can be assessed. The selection process for an interstellar crew would be, in part, a search for individuals who score highly on all of them. But there is no psychological test that can simulate 42 years. There is no way to know, in advance, how a person will change over 4 decades of confinement. The person who boards the vessel at 30 is not the person who will be aboard at 50 or 60 or 70. Life changes people. Grief changes people. Disappointment changes people. The slow accumulation of difficult years changes people in ways that no selection test can anticipate. Let us consider the structure of authority and governance aboard the vessel, because it is a problem that has no clean solution. A mission of this duration and complexity requires clear decision-making authority. When a system fails, when a medical emergency occurs, when a conflict between crew members threatens the function of the team, someone must have the authority to make decisions and the means to enforce them. This is not controversial. It is simply how complex operations in dangerous environments work. But authority on an interstellar vessel is authority without any external check. There is no oversight body to appeal to. There is no institution capable of intervening if authority is abused. The crew that boards the vessel at Earth will be, within a few years, the most isolated group of human beings who have ever lived, accountable to no one but themselves. History offers few reassuring examples of what happens to isolated groups with unchecked authority. Antarctic expeditions in the heroic era, the early 20th century, before radio communications sometimes fractured catastrophically under the pressure of isolation and poor leadership. The 1898 Belgica expedition, trapped in Antarctic ice for 13 months, saw the crew descend into a state of psychological deterioration so severe that the ship's doctor, Frederick Cook, later described it as a collective madness. The commander became increasingly erratic. Conflicts multiplied. Several men developed what we would now recognize as severe depression, and one suffered a complete psychiatric breakdown. The Belgica had 12 men and 13 months. The interstellar mission has potentially 100 people and 42 years. Governance frameworks for such a mission would need to be extraordinarily carefully designed. A command structure that prevents paralysis in emergencies, combined with democratic mechanisms for collective decisions about quality of life, resource allocation, and the social rules that govern daily existence. Systems for mediating conflicts that do not rely on the goodwill of any single individual. Mechanisms for removing a leader who has become dangerous or dysfunctional, and for replacing them without creating a power vacuum that destabilizes the crew. None of this is impossible. Human societies have spent millennia developing governance structures for exactly these kinds of challenges, but those structures all assume a baseline of options that do not exist on an interstellar vessel. On Earth, a person who cannot coexist with a community can leave it. A leader who becomes tyrannical can be deposed and exiled. A criminal can be imprisoned. On an interstellar mission, exile does not exist. Prison consumes resources and generates resentment without solving the underlying problem, and removing a leader creates a crisis of authority that must be managed without any external institution to legitimize the successor. The most extreme scenario, and it must be acknowledged, because mission planners who ignore extreme scenarios are planning failures, is an individual who becomes genuinely dangerous to others. Violent, or psychotically unstable in ways that cannot be managed medically with available resources. On Earth, such an individual is contained by law enforcement, psychiatric facilities, the full apparatus of civil society. On an interstellar vessel, the options are sedation, permanent confinement, or death. Each of these options carries consequences so severe that merely listing them reveals the depth of the problem. This is not a reason not to go. It is a reason to plan with exceptional care, to select crew with exceptional rigor, to design governance structures with exceptional thoughtfulness, and to accept that even with all of this, things will go wrong in ways that cannot be anticipated, because 42 years is long enough for almost anything to happen. Love will happen aboard this vessel. This is not speculation. It is as certain as the degradation of bone density or the accumulation of radiation damage. Human beings form emotional and romantic attachments. Place 100 of them in close quarters for 42 years, and attachments will form, deepen, and in some cases end. Romantic relationships aboard the vessel would be, in many ways, a source of profound psychological sustenance. The bond between two people who have shared the weight of this journey, who have watched each other age, who have supported each other through loss and fear, and the long monotony of the middle years, would be forged under conditions of intimacy that most human relationships never experience. The Antarctic winter-over experience suggests that close relationships are among the most powerful protective factors against the psychological erosion of isolation. People who have a strong personal bond with at least one other member of the team show markedly better psychological outcomes across all measures. But relationships also end. They fracture under the weight of years, under incompatibilities that only reveal themselves over time, under the grinding pressure of circumstances that allow no relief. And when a relationship ends on an interstellar vessel, the former partners cannot simply put distance between themselves. They will pass each other in the same corridors, eat in the same spaces, work the same shifts, breathe the same recycled air, for years, possibly for decades. The psychological cost of this, of being unable to escape someone you once loved and now cannot be near without pain, is not something that can be fully prepared for. Counseling helps. Thoughtful crew scheduling helps. But no intervention fully resolves the problem. It is simply one of the human costs of the journey, paid in private, day after day, in the small agonies of proximity without intimacy. And then there are children. Whether children are born aboard an interstellar vessel is a question that cannot be resolved by policy alone. Biology is persistent. Even with reliable contraception and over 42 years, contraception will not be perfectly reliable for all crew members at all times pregnancies will occur. The mission planners must therefore confront a question that is simultaneously medical, ethical, and existential. What does it mean to bring a child into existence on this vessel? The child did not choose this journey. They will grow up in corridors, in artificial light, breathing recycled air, eating hydroponic crops, surrounded by a fixed population of people who are, effectively, their entire world. They will learn about Earth from recordings and stories, the way children in every culture learn about a mythological homeland they have never seen. Earth will be, to them, not a home but a legend, a place that exists in the past, unreachably far away, described by adults who remember it with a nostalgia the child cannot share. Is this a harm, or is it simply a different kind of life constrained in some ways, but rich in others? A child raised aboard this vessel will grow up surrounded by some of the most intellectually accomplished and carefully selected human beings ever assembled. They will receive an education of extraordinary depth. They will have a role, a genuine, essential role in a project of historic importance. They will know from the beginning that they are part of something that matters, but they will also never feel rain. They will never stand in an open field and watch the sky change. They will never experience the specific texture of a world that evolved over billions of years to support life like theirs. These experiences, which most humans take entirely for granted, will be permanently inaccessible to them, not because of any choice they made, but because of the choice made by the adults who brought them into being in this place. The ethical weight of this is real. It has no clean resolution. It is one of the genuinely unresolvable tensions of interstellar travel, the collision between human biology and human aspiration, between the future the mission is trying to reach and the present it creates along the way. Consider now the particular cruelty of communication delay. In the first weeks of the mission, the spacecraft is still within the inner solar system. Radio signals travel at the speed of light, and Earth is minutes away in light travel time. A message sent from the vessel reaches Earth in 10 minutes, 20 minutes, an hour. Conversation is still recognizable as conversation. You can send a message and receive a response within the same day. As the vessel moves outward, the delay grows. Past the orbit of Jupiter, Earth is perhaps 40 minutes away by light. Past Saturn, over an hour. By the time the vessel has reached the outer edge of the solar system, the heliopause, the boundary where the sun's influence gives way to interstellar space, Earth is roughly 20 light hours away. A message takes 20 hours to arrive. A response takes 20 hours to return. A single exchange of messages occupies nearly 2 days. And then the vessel enters interstellar space, and the distance begins to accumulate in light years rather than light hours. 1 year into the interstellar journey, assuming a velocity of 10% of light speed, the vessel is approximately 0.1 light years from Earth. Signals take just over a month each way. By year 5, the round-trip communication time is approximately 1 year. By year 20, it is 4 years. By the time the vessel arrives at Proxima Centauri, a single question sent to Earth and answered will take more than 8 years to complete. This is not communication in any meaningful sense. It is correspondence. Letters across an abyss of time, written to people who will be significantly older or gone by the time the reply arrives. The crew sends a message describing a medical crisis. By the time Earth's physicians respond with advice, the patient has either recovered or died. The crew asks a question about a navigation anomaly. By the time the answer arrives, the anomaly is 4 years in the past. Earth recedes not just in distance but in relevance. The events of terrestrial life, political upheavals, technological breakthroughs, cultural shifts, the births and deaths of people the crew knew and loved, arrive years late, out of context, stripped of the immediacy that makes news meaningful. A crew member receives word that a parent has died. The parent died 4 years ago. The grief is real and immediate, but the event is ancient. There was no chance to say goodbye, no way to be present, no possibility of any response other than a message sent into the dark that will arrive 4 years hence, at a world that has already moved on. By the midpoint of the journey, Earth has become something like a historical society for the crew, a place that exists in memory and in recordings, increasingly distant from lived experience. The crew's children, born aboard the vessel, have no personal memory of Earth at all. For them, the messages from Earth are messages from a foreign civilization. Interesting, perhaps, but not home. Home is here. Home is the corridor, and the hydroponic bay, and the rotation of the habitat ring, and the faces they have known since birth. The gradual severance from Earth is not a single dramatic event. It is a slow erosion, month by month and year by year, until the thread between the vessel and its origin has stretched so thin it carries almost no weight at all. And yet people will volunteer for this. People are volunteering in a sense right now, not literally, because the mission does not exist yet, but in the deeper sense that the individuals who will one day form this crew are already forming. They are the people who lie awake at night, thinking about what is out there, who feel, when they look at the stars, not comfort but hunger, who find in the vastness of the universe not diminishment but invitation. What drives a person to accept this? Not abstractly, not in the way we discuss human motivation in psychological journals, but in the concrete, personal, irrevocable sense of standing before a boarding ramp and choosing to walk up it. The Antarctic winter over volunteers have been studied extensively, and what emerges from this research is a consistent profile. These are people with an unusually high tolerance for uncertainty. They do not need to know how things will turn out. They are comfortable making decisions with incomplete information, comfortable living with outcomes they cannot control. They have strong internal sources of meaning. Their motivation comes from within, from the work itself, and from their sense of identity as someone who does difficult things. rather than from external validation or the approval of others. They also tend, counterintuitively, to have a high capacity for acceptance. Not passivity, these are not passive people, but the ability to accept what cannot be changed, to release the desire to control circumstances that are beyond control, and to find within that acceptance a kind of freedom. The Antarctic winter over, the submarine crew member on a 6-month deployment, the cosmonaut on a year-long mission to the ISS, all of them describe, in retrospect, a quality of focus that their normal lives did not contain. A clarity that came from the elimination of alternatives. When you cannot leave, you stop spending energy wishing you could, and you put that energy into being where you are. Over 42 years, this quality, this capacity for presence, without alternative, would be tested beyond anything any psychological study has been able to measure. It would be pushed to its absolute limit, and in some people it would break, and those people would spend years in a darkness that no amount of artificial lighting could address. And in other people, it would become something extraordinary, a depth of engagement with existence that most human beings never reach, because most human beings are never forced to. The interstellar journey strips away everything that is not essential. Everything that can be postponed, avoided, distracted from all of it becomes unavoidable. You cannot scroll through your phone. You cannot go for a drive. You cannot lose yourself in the crowd of a city or the noise of a busy world. There is only the vessel, the journey, the people around you, and the question of what you are doing with the time you have. Some people would find, in that stripped-down existence, a kind of peace, a recognition of what actually matters, unobscured by everything that normally obscures it. They would arrive at Alpha Centauri, not diminished by the journey, but deepened by it, carrying within them a quality of experience that no human being who stayed on Earth could fully comprehend. Others would arrive broken, or would not arrive at all. This is the true cost of the journey. Not the fuel, not the engineering, not the radiation. The cost is measured in human lives, not necessarily in deaths, though there will be deaths, but in the years consumed, in the relationships abandoned, in the selves that are transformed beyond recognition by 42 years of the most extreme isolation in human history. It is a cost that cannot be calculated in advance. It can only be paid day by day, in the dark, between the stars. There is one more dimension of this isolation that deserves careful attention, because it is the dimension that makes interstellar isolation categorically different from every other form of isolation humans have studied. It is the knowledge that you cannot go back. In every isolated environment that has ever been studied, every Antarctic station, every submarine, every space mission, every simulated isolation experiment, the subjects know that the isolation will end. The winter over team counts the days until the aircraft returns. The submarine crew knows when they will surface. The ISS astronaut has a Soyuz capsule docked to the station, capable of returning them to Earth in 3 hours in an emergency. This knowledge, the existence of a return, the presence of an exit, functions as a psychological anchor of extraordinary power. It does not eliminate the stress of isolation, but it provides a framework within which that stress can be endured. Remove the anchor entirely, and you are in territory that has never been studied. No human being has ever been placed in a situation where return was genuinely, physically impossible. We have no data on what that does to the human mind over timescales measured in decades. We have theories, extrapolations from the ICE environment literature, informed speculation from psychiatrists who have studied extreme situations, but we do not know. What we can say, based on what we understand of human psychology, is that the knowledge of no return would function differently for different people at different stages of the journey. In the early years, it might be manageable, the excitement of the mission, the novelty of the experience, the sense of historic purpose, all provide insulation against the full weight of the commitment. But as years pass and the mission becomes routine, as the initial cohort of crew members ages and some of them begin to die, as the accumulated losses of a lifetime lived away from Earth begin to pile up in those years, the no-return reality would press with increasing weight on every member of the crew. Some would make peace with it. They would find, in the irreversibility of their choice, a kind of clarity. They are here. They cannot be anywhere else. The only question is what to do with that fact. Others would not find peace. They would carry the grief of what they left behind for decades, a wound that does not close because the situation that caused it does not change. They would mourn Earth the way people mourn the dead acutely at first, then in waves, then as a constant low-level presence that colors everything. And some, and this must be said clearly, because it is true, would reach a point where they could no longer continue, where the accumulated weight of years of confinement and loss and irreversibility became more than they could carry. The incidence of depression and suicidal ideation in extreme isolation environments is not zero. It is not even close to zero. On a 42-year mission with no return and no rescue, the mental health consequences of this reality would be among the most serious challenges the crew would face. Preparing for this is not defeatism, it is honesty. It is the same honesty that drives mission planners to prepare for micrometeorite impacts and reactor failures. The human mind, like any critical system, can fail. And when it fails in interstellar space, the consequences are no less serious than when the life support does. The vessel carries physicians for the body. It must carry equally skilled practitioners for the mind. And it must carry a culture, rituals, art, music, stories, the accumulated wisdom of how human communities sustain themselves through the hardest things that provides each crew member with something to hold on to on the nights when the darkness presses closest. Because there will be those nights. 42 years is long enough to guarantee them. And there will also be other nights. Nights when a crew member stands at a viewport and watches the stars different from any view seen from Earth. The constellations shifted, the familiar patterns dissolved, the sky belonging entirely to this vessel and no one else, and feels something that has no name in any human language. Something that is not quite wonder, and not quite grief, and not quite gratitude, but contains elements of all three. The feeling of being exactly where you are, in the dark, moving, towards something that no human eye has ever seen up close. Those nights, too, are part of the 42 years. They may, in the end, be the part that makes it survivable. After 42 years, it appears, not gradually, not with ceremony. One morning, or what the vessel's chronometers designate as morning, in the absence of any sun to mark the distinction, a crew member at the telescope array notices something that has been invisible for the entire journey. A disk. Not a point of light, but a disk. Small, still smaller than a full moon seen from Earth, but unambiguously extended, unambiguously three-dimensional, a sphere of gas and rock and whatever lies beneath, hanging in the dark at a distance that is, for the first time in 42 years, measurable in something other than light years. The announcement goes through the vessel like a current. 42 years of corridors and recycled air, and the same faces aging imperceptibly day by day. 42 years of messages from Earth arriving years late, of watching children grow up who have never felt gravity except the artificial kind, of maintaining systems and managing conflicts, and enduring the grinding weight of time in a closed space. 42 years of moving toward a point of light that never seemed to grow closer, because stars are so far away that even at 10% of light speed, the apparent change in their positions accumulates with agonizing slowness. And now it is there, real, close enough to show a disk. What the crew sees in their telescopes in those final weeks of approach is both extraordinary and, in its specific details, deeply sobering, because Proxima Centauri b is not the world that the hopeful projections of the early 21st century imagined. It is something more complicated, more alien, and in certain respects, more hostile than any surface human beings have ever attempted to inhabit. Let us look at it carefully. Let us look at what the data actually says. Proxima Centauri is a red dwarf. This classification, red dwarf, sounds almost benign, as though the diminutive adjective describes something gentle, something smaller and therefore less threatening than the stars we associate with power and heat. This impression is incorrect. Red dwarfs are the most common type of star in the galaxy. Approximately 70% of all stars are red dwarfs. They are small. Proxima Centauri contains only about 12% of the Sun's mass, and they are cool, with surface temperatures roughly half that of the Sun. They burn so slowly and so efficiently that they will remain on the main sequence, the stable, hydrogen-fusing phase of stellar life, for trillions of years. Our Sun will exhaust its hydrogen fuel in approximately 5 billion years. Proxima Centauri will still be fusing hydrogen 4 trillion years from now, long after the universe has become a far colder and emptier place. In terms of longevity, red dwarfs are the universe's most durable stars. But longevity is not the same as hospitability, and for a planet orbiting close enough to a red dwarf to receive adequate warmth, the star's other characteristics become deeply relevant. Proxima Centauri is a flare star. This means it is subject to sudden, violent releases of energy, stellar flares, far more frequently and far more intensely than our Sun. A solar flare from our Sun is a dramatic event, capable of disrupting satellite communications, inducing currents in power grids, and producing auroras visible at mid-latitudes. A major flare from Proxima Centauri is something categorically different. In March of 2016, a team using the Everescope telescope array detected a superflare from Proxima Centauri, with an energy output roughly 10 times greater than the most powerful solar flare ever recorded from our Sun. The ultraviolet radiation flux reaching Proxima Centauri b during this event was estimated to be approximately 65 times the level that would be required to be lethal to unprotected terrestrial bacteria. This was not an anomalous event. Analysis of Proxima Centauri's behavior over extended observation periods suggests that superflares of this magnitude occur approximately 5 times per year. Smaller but still significant flares occur far more frequently, potentially dozens of times per day. Every time a flare erupts, a wave of ultraviolet radiation and energetic charged particles washes over Proxima Centauri b. Without protection, a surface organism exposed to this radiation would not survive. The DNA damage would be rapid, catastrophic, and irreparable. The ultraviolet flux alone during a major flare would be sufficient to sterilize exposed surfaces within minutes. This is the environment that greets the crew when they arrive. Proxima Centauri b orbits its star at a distance of approximately 4.6 million miles, about 7.5 million kilometers. This sounds close, and relative to Earth's distance from the Sun, approximately 93 million miles, it is extraordinarily close. The planet completes one full orbit every 11.2 days. Its year is 11 days long. At this distance, the planet almost certainly exhibits a phenomenon called tidal locking. The same gravitational forces that have locked the Moon so that it always shows the same face to Earth. The result of the Moon's rotation rate being brought into synchrony with its orbital period by tidal friction over billions of years have, over the lifetime of the Proxima system, locked the planet's rotation to its orbital period. One side of Proxima Centauri b faces the star permanently. The other side faces permanently away, into the darkness of space. The implications of this are profound and strange. On the day side, the hemisphere of permanent noon, the star hangs motionless in the sky, approximately 3 times larger in apparent diameter than our Sun appears from Earth, casting a deep red light over a landscape that never experiences night. The surface temperature here, depending on atmospheric properties, could be extremely high. Without a substantial atmosphere to redistribute heat, surface rocks on the day side might be hot enough to glow. On the night side, the reverse. Permanent darkness, permanent cold. Without atmospheric heat transport, temperatures would fall toward the temperature of deep space hundreds of degrees below zero. Any volatiles, water, carbon dioxide, nitrogen would freeze and remain frozen, locked in perpetual ice. Between these two extremes lies the terminator, the boundary between permanent day and permanent night, a narrow ring encircling the planet where the star hangs perpetually on the horizon, where temperatures might be moderate, where liquid water, if any exists on the planet, might be found. This region, sometimes called the Ring of Life in discussions of potentially habitable tidally locked worlds, is where any surface life would need to exist, and where any landing mission would need to target. But the terminator is not a gentle environment. The temperature gradient between the blazing day side and the frozen night side drives powerful atmospheric circulation. Hot air rises on the day side, flows at altitude toward the night side, cools and descends, then returns along the surface. This creates permanent, powerful winds at the terminator, steady flows that may reach hurricane force, blowing continuously from day side to night side along the surface and from night side to day side at altitude. Landing in this wind regime would be technically demanding. Operating on the surface would require equipment designed to function in sustained high winds continuously. The James Webb Space Telescope, launched in December of 2021, has transformed our ability to study the atmospheres of exoplanets. By observing the light from a star as its planet passes in front of it and analyzing which wavelengths are absorbed by the planetary atmosphere, astronomers can determine what molecules are present. For Proxima Centauri b, this technique is complicated by the fact that the planet does not transit. It does not pass in front of its star from Earth's perspective, making direct atmospheric characterization with current technology extremely difficult. What we can say, based on current models and indirect constraints, is that Proxima Centauri b may or may not have retained a substantial atmosphere. The stellar wind from Proxima Centauri, the continuous flow of charged particles streaming outward from the star, is intense at the planet's orbital distance, several thousand times the intensity of the solar wind at Earth's location. Over billions of years, this wind, combined with the frequent flare activity, would have subjected the planet's atmosphere to extreme erosion. Unless the planet has a strong global magnetic field to deflect the incoming particles as Earth does, generated by the convective motion of its molten iron core, the atmosphere may have been substantially or entirely stripped away. Earth's magnetic field is not a guarantee that comes with rocky planets. It requires a planet with a differentiated interior, a metallic core, still partially molten, large enough and rotating fast enough to generate a substantial dynamo effect. Whether Proxima Centauri b has such an interior is unknown. The models suggest it might, but the uncertainty is large. A planet without an atmosphere and without a magnetic field, orbiting a flare star at close range, is not a world with surface life. It is a radiation-scoured rock, its surface sterilized by decades and centuries and millennia of unfiltered ultraviolet and particle radiation, its potential for liquid surface water eliminated by the absence of atmospheric pressure. This may be what the crew finds: a silent, barren surface, baking on one side and frozen on the other, swept by perpetual winds at the terminator, offering nothing that a human being can use without extraordinary technological mediation. And yet, the history of life on Earth offers a perspective that complicates simple pessimism. Life on Earth did not wait for comfortable conditions. It found a way into every environment we once thought inhospitable. Hydrothermal vents on the ocean floor, where water at several hundred degrees Celsius emerges from the crust under enormous pressure, host rich communities of organisms, bacteria, archaea, tube worms, crustaceans that derive their energy not from sunlight, but from the chemical reactions between superheated water and the minerals it carries. These organisms were discovered only in 1977, and their existence fundamentally altered our understanding of the range of conditions under which life is possible. Microorganisms have been found living in the cores of Antarctic glaciers, in highly acidic hot springs, in the high radiation environment of nuclear reactor cooling pools, in the upper atmosphere at altitudes once thought too cold and UV intense for survival. The more extreme the environment we examine, the more often we find life has found a way in. For Proxima Centauri b, the most hopeful scenario involves not the surface, but the subsurface. If the planet retains internal heat from radioactive decay in its crust, from tidal flexing induced by its star's gravity, from residual heat of formation, then liquid water might exist below the surface, insulated from the radiation environment above by kilometers of rock or ice. Subsurface oceans, sealed away from the flares in the stripped atmosphere, heated from below rather than above. This is not a speculative idea invented to preserve hope. Subsurface liquid water exists in our own solar system, almost certainly beneath the ice shells of Europa, Enceladus, and Ganymede, and possibly beneath the surface of Mars. The conditions for subsurface liquid water are less restrictive than the conditions for surface liquid water. They do not require a strong magnetic field, they do not require a dense atmosphere. They require only sufficient internal heat and a sufficient depth of overlying material to provide insulation. Whether Proxima Centauri b has these conditions is unknown. We cannot know from Earth. We can model it, constrain the parameters, develop probability estimates, but the question cannot be answered from a distance of 4.24 light-years with the instruments available to us today. It can only be answered by going there. The approach to the system takes months. The vessel, decelerating now using whatever mechanism its engineers designed for the purpose, watches the system grow from a disk to a visible sphere to a world with features. The magnetic sail, deployed weeks earlier, catches the sparse stellar wind of Proxima Centauri and converts the vessel's residual velocity into heat that radiates away from the trailing panels. The deceleration is gentle but continuous, and the crew feels it as a slight, persistent heaviness, the sensation of gravity slightly stronger than the rotation provides, from a direction that shifts as the vessel changes its orientation. The star, seen from this distance, is remarkable. Not the blazing white-yellow disk of the sun viewed from Earth's distance, but a deep, ruddy orange, almost red, 3 times larger in apparent size than the sun appears from home, hanging in a sky that is not quite black, but a deep, saturated crimson at its edges. The light it casts is warm in color but low in luminosity, a perpetual late afternoon red that covers everything it touches. The planet, when it comes into full resolution in the telescope arrays, is visually striking in a way that is difficult to describe without anthropomorphizing. It looks wrong. Not wrong in the way of a mistake, but wrong in the way that any deeply alien thing is wrong correct by its own logic, coherent within its own set of rules, but fundamentally unlike anything in human visual experience. The day side is bright, almost painfully so, through unfiltered sensors rock. And here, something unexpected, a faint, pale sheen across portions of the sunlit hemisphere that the spectrographic analysis will later confirm is ice. High-altitude ice, deposited by the atmospheric circulation, persisting in regions where the angle of the star's light is oblique enough that equilibrium temperatures remain below freezing even on the permanent day side. The night side is a flat darkness, featureless at visible wavelengths, but alive in infrared thermal imaging, reveals a landscape still shedding heat, absorbed over billions of years, glowing faintly at temperatures that suggest the interior is not dead. And the Terminator. The crew who first sees the Terminator in full resolution, the boundary between permanent day and permanent night, running as a ragged, complex line around the planet's circumference, falls silent, because the Terminator is not a simple edge. It is a dynamic, complicated boundary where the atmospheric circulation meets itself, where winds from opposite directions collide, where clouds form and dissipate in patterns that bear a disturbing resemblance to the weather systems of Earth seen from orbit. There are clouds, not everywhere, not in the abundance of Earth's atmosphere, but unmistakably present condensed water vapor, or water ice crystals, catching the oblique light of the star and scattering it in ways that are immediately, viscerally familiar to a crew that has spent 42 years dreaming of the sky. Clouds mean water vapor. Water vapor means water, not necessarily liquid water on the surface, not necessarily abundant water, but water present in the atmosphere, participating in a weather cycle of some kind. The spectrographic analysis of the atmosphere, conducted over days of careful observation, reveals a composition that is neither Earth-like nor entirely hostile. Nitrogen is present in substantial quantities, carbon dioxide, water vapor confirmed, and then, buried in the noise of the data, something that takes 3 days of analysis to confirm and that sends the scientific team into a state of barely controlled excitement. Methane. Methane is a molecule with a short atmospheric lifetime. Ultraviolet radiation from the star, even the filtered, attenuated ultraviolet that reaches the lower atmosphere, breaks it down on timescales of decades. The presence of methane in the atmosphere of Proxima Centauri b means that something is continuously replenishing it. On Earth, methane is replenished primarily by 2 sources: geological activity and life. This is not proof of life. Geological methane production is well documented in environments with no biological activity. Active volcanism, serpentinization reactions in the crust, hydrothermal systems, all of these can produce methane abiotically. The detection of methane is not a discovery of life. It is a signal that something interesting is happening and that the source must be identified. The crew prepares probes, small hardened vehicles designed to survive entry into the atmosphere, landing on the surface and operating for weeks or months in conditions that have been modeled but never directly measured. Each probe carries a suite of instruments: cameras, mass spectrometers, gas analyzers, seismometers, ground-penetrating radar, and a drill capable of extracting core samples from a depth of several meters. The first probe targets the terminator region, landing in a site chosen for moderate temperatures, relatively low wind speeds based on atmospheric modeling, and the presence of what the radar suggests is a shallow subsurface reflector, consistent with ice or liquid water. The descent takes 40 minutes. The probe enters the atmosphere at high velocity, the heat shield glowing white-hot as it bleeds off kinetic energy, the parachute deploying at altitude, the retrorockets firing in the final seconds to lower it gently onto the surface. Contact is maintained throughout. The crew watches through the probe's cameras as the landscape comes up to meet it. The surface of Proxima Centauri b, seen for the first time at ground level, is composed of dark volcanic rock, fractured and layered, in places covered by a thin deposit of rust-colored dust. The light from the star, hanging low on the horizon, turns everything the color of dried blood. The sky directly overhead is darker than Earth's sky at any time, except deep night, the atmosphere too thin to scatter much light. But at the horizon, where the star's light enters at a low angle through a greater depth of atmosphere, there is a band of deep orange that creates an effect of permanent, dramatic sunset. The wind is present, as predicted. Not catastrophic at this location, the models were accurate but steady, a constant 40 kilometers per hour from the direction of the dayside, carrying fine dust that accumulates against the rocks in drifts. And then the probe's spectrometer begins returning data from the surface soil. The results take several hours to fully analyze. The crew knows, from the pace at which the science team is working, that something significant has been found. There is a quality of focused intensity in the research that spreads to the rest of the crew, a held breath that extends for hours. When the lead scientist calls the crew together to share the findings, the room is entirely silent. The soil of Proxima Centauri b contains organic compounds, complex organic compounds, amino acids, or molecules with the same structural signature as amino acids, produced by processes that the abiotic chemistry of rocks and ultraviolet radiation can generate under the right conditions. This, alone, would not be remarkable. Amino acids form abiotically throughout the universe. They have been found in meteorites, in interstellar molecular clouds, on the surfaces of comets. Their presence in the soil tells us nothing definitive about life. But the probe also found something else. In a layer of rock approximately 2 meters below the surface, old rock, the drill's analysis suggests, deposited hundreds of millions of years ago, there are structures, microscopic structures, visible in the probe's highest resolution imaging, that are not minerals. They are too complex, too regular, too inconsistent with any known abiotic process to be anything other than what they appear to be. Fossilized microorganisms. Not life, not current life, not anything that is alive right now or that has been alive for a very long time, but the remains of life organisms that existed on the surface or in shallow subsurface environments of Proxima Centauri b hundreds of millions of years ago, before the star's increasing flare activity, or the loss of the magnetic field, or some other catastrophic change, drove them to extinction or drove them deeper. Life arose here. In another star system, orbiting a different sun, under conditions profoundly different from those of Earth, the chemistry of carbon and water found a way to organize itself into something that could grow and replicate and leave behind, in the rock record, the traces of its existence. We are not the only world that has ever known life. The implications of this discovery take time to process, even for people who have spent 42 years preparing for the possibility. There is a difference between knowing intellectually that life might have arisen elsewhere and holding in your hands, or rather, receiving in your data streams the evidence that it did. It changes the context of everything. Every other star, every other planet, every dark and silent world in the galaxy must now be reconsidered in the light of this data. If life arose on Proxima Centauri b with its flare star, its tidal locking, its thin and battered atmosphere, then the conditions required for life to begin are far less restrictive than the conservative models predicted. The universe is not a nearly sterile place with occasional islands of biology. It is a place where life emerges, wherever chemistry and energy and time converge in the right proportions. Which means there are other worlds, many other worlds, some of them perhaps where life did not go extinct, where the star was stable enough, the magnetic field strong enough, the atmosphere thick enough, for life not just to begin but to persist, to complexify, to evolve over billions of years toward forms we cannot anticipate. The crew of the first interstellar mission sits with this knowledge in the red light of a foreign star, surrounded by the silence of a world that life abandoned long ago, and feels the weight of what they have found. They have not found life. They have found its shadow, its residue, the record of an experiment that the universe ran and then, for reasons the geologists and astrobiologists aboard will spend decades trying to understand, terminated. But an experiment that ran, that succeeded, for a time, that left its mark. And if it ran here, it runs elsewhere, in systems we have not visited, on worlds we have not named, around stars whose light has not yet reached Earth. The galaxy is not empty. It is full of stories, full of experiments in chemistry and biology and time, each one running its own course, each one either still in progress or already concluded, each one leaving its record in the rock and the atmosphere and the chemical signatures that patient instruments can read. The crew has traveled 4.24 light-years to find the beginning of this understanding. It is not the answer. It is something better than an answer. It is the knowledge that the question is real, that life is not a miraculous anomaly on a single blue world, but a recurring theme in the chemistry of the universe, playing out across scales and distances and time spans that dwarf any framework the human mind evolved to work with. They look up from their data. They look out the viewports. The star hangs on the horizon, deep, red and steady, not flaring now, calm in this moment, as indifferent to their presence as it was to the microorganisms whose fossils they have just found. The landscape extends to the horizon in silence. The wind moves dust across the rocks. The sky at the edges glows orange. It is the most alien thing any human being has ever seen. And it is, in the only way that ultimately matters, familiar. Life was here. That is enough. For now, that is enough. Before the vessel ever leaves Earth's orbit, before a single crew member steps aboard, before the first reactor is fueled or the first hydroponic bay is seeded, a question must be answered that has nothing to do with physics or engineering or the biology of long-duration spaceflight. Who decides to go? Not who goes. That is a question of selection, of psychological assessment and medical screening and years of training. The deeper question is, who decides that the mission happens at all? Who determines that the resources required, the industrial capacity, the decades of preparation, the human lives consumed in the attempt are worth committing to this specific purpose, rather than to any of the countless other purposes that compete for them? This is not a technical question. It is a moral one, and it has no clean answer. Consider the scale of what we are discussing. The International Space Station, the most complex and expensive structure humanity has ever built, cost approximately $150 billion over roughly 15 years of construction and operation, funded by a coalition of 15 nations. It carries a crew of 6. It orbits at an altitude of approximately 400 kilometers. It is resupplied roughly 8 times per year, and it represents the outer boundary of current human spaceflight capability, the furthest we have consistently maintained a human presence beyond Earth's surface. An interstellar mission to Alpha Centauri would require a vessel orders of magnitude larger and more complex than the International Space Station. It would require a propulsion system that does not yet exist. It would require decades of preparation and assembly in orbit. It would carry a crew of perhaps 100 people for 42 years with no resupply, no rescue, and no return. Conservative estimates for the total cost of such a mission, factoring in propulsion development, vessel construction, crew training, mission support infrastructure, and the decades-long operational commitment, run into the tens of trillions of dollars. For context, the gross domestic product of the entire United States in a recent year was approximately $25 trillion. An interstellar mission might cost the equivalent of several years of the total economic output of the world's largest economy. This is not money that any nation spends on a single project. It is not money that any corporation commands, regardless of the ambitions of its founders. It is money that can only be mobilized through a degree of international cooperation that has no precedent in human history. A commitment sustained not over years or decades, but over generations, insulated from the political cycles and economic fluctuations and shifts in public priority that have derailed every large-scale, long-term human project ever attempted. The Apollo program, humanity's most audacious act of exploration to date, was conceived, executed, and concluded within approximately a decade. It was sustained by a specific geopolitical context, the Cold War competition between the United States and the Soviet Union, that provided the political will to maintain funding through multiple administrations. When that context changed, when the moon landings became routine rather than competitive, funding evaporated. The program ended. The hardware was mothballed, the engineers dispersed, and for the next half-century, no human being traveled beyond low Earth orbit. An interstellar mission cannot be built on geopolitical competition. The timescales are too long, the costs too diffuse, the benefits too distant. It requires a motivation that transcends any particular political moment, a motivation rooted not in competitive advantage, but in something deeper, something that speaks to what humanity is and what it intends to become. Whether that motivation currently exists in a form robust enough to sustain a centuries-long commitment is a question worth examining honestly. The argument against the interstellar mission begins with a simple observation. The world has problems, immediate, pressing, solvable problems that cause immeasurable suffering to living human beings right now. Approximately 700 million people live in extreme poverty, surviving on less than $2 per day. Preventable diseases kill millions of children annually in regions where the medical infrastructure to treat them is simply absent. Climate change is reshaping the planet's habitability in ways that will displace hundreds of millions of people over the coming century. Biodiversity is collapsing at a rate not seen since the mass extinction events of the geological past. The gap between what humanity could do to address these problems and what humanity actually does is not primarily a gap of knowledge or technology, it is a gap of priority and will. Against this backdrop, the proposal to spend tens of trillions of dollars sending 100 people to another star system, a journey that will take 42 years, that will yield no material return, that will benefit no living person on Earth in any direct or immediate sense, can seem not merely impractical but morally obscene. This argument has force. It cannot be dismissed with a wave of the hand and an invocation of human destiny. Every dollar committed to an interstellar mission is a dollar not committed to a malaria vaccine or a desalination plant or a flood barrier or a school. The opportunity cost is real. The people who would have been helped by those resources are real. Their suffering does not become less real because the interstellar mission is grand and historic and scientifically significant. And yet the argument against exploration is not new. It has been made against every major act of human exploration in history, and it has always been wrong in ways that were not immediately visible. When the Portuguese crown debated whether to fund Vasco da Gama's voyage around the tip of Africa in the 1490s, the objection was the same in structure, if not in scale. The resources could be better spent at home. The outcome was uncertain. The potential benefit was speculative. And yet the voyage happened, and the route it established connected the economies of Europe and Asia in ways that transformed both, generating wealth and knowledge and cultural exchange that would have been impossible to predict from the perspective of the 1490s skeptic. When the United States Congress debated funding the Apollo program in the early 1960s, the same argument was made. The country had domestic needs. The money could feed children, build hospitals, fund schools. The moon was a rock. What possible benefit could justify the cost? The benefit, as it turned out, was not primarily the moon rocks, though those were scientifically invaluable. It was the technology developed to get there, technologies that became the foundation of the modern semiconductor industry, of satellite communications, of the global positioning system, of the medical imaging tools that now save millions of lives annually. None of this was predictable in advance. Exploration generates knowledge, and knowledge generates applications, and applications generate benefits that flow back to precisely the people whose immediate suffering was cited as a reason not to explore. This is not a guarantee. Not every act of exploration generates proportional downstream benefit, but the historical pattern is consistent enough to carry epistemic weight. More fundamentally, the argument that humanity must choose between exploration and addressing suffering rests on a false premise. The total economic output of humanity is not a fixed pie, divided between the stars and the poor. It is a growing quantity, shaped by investment and innovation and the accumulation of knowledge. An interstellar mission does not consume resources that would otherwise flow to poverty relief. It generates the scientific and technological development that expands the total resource base from which all human needs are met. But this argument, however valid, does not fully settle the moral question, because the people who would benefit from the downstream technology of an interstellar mission are future people, people who do not yet exist, who have no voice in the decision, whose interests cannot be weighed in any practical political calculation against the interests of people who are suffering now. The ethics of intergenerational commitment of sacrificing present welfare for future benefit is genuinely complex, and anyone who pretends it is simple is not engaging honestly with the question. There is a second moral dimension to the interstellar mission that is distinct from the resource allocation question, and in some ways more troubling. It is the question of the crew. The people who board this vessel are volunteers. They have been selected, trained, informed of every risk in exhaustive detail. They are adults making free choices about their own lives. The principle of individual autonomy, the right of a person to determine the course of their own existence, to accept risks that others might not accept, to pursue goals that others might not pursue, is among the most fundamental values in any ethical framework that takes human dignity seriously. And yet, the commitment required of the crew of an interstellar mission is not comparable to any other voluntary risk that human beings accept. A mountaineer who attempts Everest risks death, but the attempt lasts weeks. A test pilot risks death on every flight, but the risk is intermittent, and the pilot goes home between flights. An astronaut on a long-duration mission to Mars risks death and accepts 6 months to a year of isolation, but knows that home is reachable and return is coming. The interstellar crew accepts not weeks or months of risk, but a lifetime. They accept not intermittent hardship, but continuous, permanent confinement. They accept not a delayed return, but no return at all. They accept, in exchange for the opportunity to do something no human being has ever done, the entirety of their remaining years. Can a person truly give informed consent to this? Can any amount of training and preparation give a 30-year-old genuine understanding of what it means to commit the rest of their life to a metal vessel, to accept that they will never again feel open sky above them, never again see a horizon that recedes to natural distance, never again encounter a stranger or walk through a door into a room they have never been in before? The Antarctic winter-over researchers consistently report that their experience of 9 months of isolation was more intense and more difficult than they anticipated despite extensive preparation. The gap between intellectual understanding and lived experience, even for 9 months, is significant. For 42 years, that gap may be unbridgeable. The person who boards the vessel at 30 cannot fully comprehend what the person they will be at 50 or 60 will feel about the choice they made. This is not an argument against letting people choose. It is an acknowledgement that the choice carries a weight that consent processes cannot fully capture, and that anyone designing such a mission has a profound obligation to take seriously. Not to prevent the mission, but to approach the selection and preparation of the crew with a degree of ethical seriousness commensurate with what is being asked of them. There is also the question of children. We have discussed this from the perspective of the vessel, the practical and ethical challenges of raising children in an enclosed environment. But there is a prior question. The decision to create a child is made by the parents. The child who results from that decision will spend their entire life as a consequence of it, in a context they did not choose and cannot exit. This is, in one sense, true of all children everywhere. None of us chose the circumstances of our birth. None of us consented to the values instilled in us, the language we speak, the culture that shaped our earliest sense of what the world is. The children of the Interstellar mission are not uniquely wronged by being born into a context they did not choose, but the context of an interstellar vessel is not merely a culture or a language. It is a physical constraint from which there is no escape, ever. A child born on Earth into difficult circumstances can, in principle, leave. They can emigrate, can reject the culture they were raised in, can build a life categorically different from the one their birth circumstances suggested. The child born on the interstellar vessel cannot do any of these things. Their options are defined by the walls of the vessel and the population within it for the duration of their life. Whether this constitutes a harm, and if so, whether it is a harm that outweighs the value of the life itself, is a question that moral philosophers will debate, and that the people who must make decisions about the mission's reproductive policies will need to confront without the luxury of philosophical resolution. There is a calculation in the interstellar travel literature that is known informally as the weight calculation, and it poses a problem that is at once purely mathematical and deeply human. The premise is simple. Propulsion technology improves over time. A mission launched today, with current technology, travels more slowly than a mission launched in 50 years with improved technology. If the improvement is significant enough, the later mission will arrive before the earlier one, despite having launched later. The question the weight calculation asks is, given a certain rate of technological improvement, what is the optimal time to launch an interstellar mission? Launch too early, and you commit to a slow journey that will be overtaken. Launch too late, and you delay indefinitely, always waiting for the next improvement. The mathematics of the weight calculation suggest that under most reasonable assumptions about the rate of technological progress, there is an optimal launch window, a point at which waiting for better technology no longer compensates for the additional delay. The specific numbers depend on assumptions that are deeply uncertain, but the general conclusion is that indefinite waiting is not optimal, and that at some point, the benefit of launching with current technology outweighs the benefit of waiting for better technology. But the weight calculation is, at its core, an abstraction. It treats the decision to launch as a purely mathematical optimization problem, and it omits the human dimension entirely. Consider what the weight calculation means for the crew of an early mission. They volunteer, they train for years, they board the vessel. They spend 20 years in transit, enduring everything that 42 years of interstellar travel entails, sacrificing everything they sacrificed. And then they receive a message, 8 years round trip from Earth. A new propulsion system has been developed. A second mission has been launched. It will arrive before them. They will not be first. The sacrifice they made, the life they committed, will be rendered not meaningless because the data they gather still has value, because the experience still advances human knowledge, but secondary. They will arrive at Proxima Centauri to find, perhaps, that a faster vessel has preceded them by a decade, that the first footsteps on the surface were taken by someone else, that the discovery they dreamed of making has already been made. How does a person live with this? How does a crew that has sacrificed everything process the knowledge that their sacrifice was, in the final accounting, unnecessary, that if they had simply waited, someone would have arrived faster, cheaper, better equipped? There is no good answer to this question. There is only the recognition that it is a real possibility, that mission planners must acknowledge it honestly, and that the crew must be prepared, insofar as preparation is possible, for the full range of outcomes, including this one. The weight calculation is not just a mathematical tool. It is a window into one of the deepest tensions of interstellar travel, the collision between the individual life, with its finite duration and its irreversible commitments, and the long arc of technological progress, which operates on timescales that individual lives cannot encompass. And yet, set aside the economics and the ethics and the weight calculation for a moment. Set aside the political challenges and the resource allocation debates. Set aside even the question of whether the mission is justified by any rational cost-benefit analysis. Ask a different question. Ask what it means for humanity to become, for the first time in the history of life on Earth, a species that inhabits more than one star system. For approximately 3.8 billion years, life on Earth has been confined to a single planet. Through 5 mass extinctions, through the rise and fall of hundreds of millions of species, through the emergence of intelligence and technology and civilization, every living thing that has ever existed on this planet has been utterly dependent on the continued habitability of this one world. A large enough asteroid impact, a sufficiently extreme volcanic episode, a runaway greenhouse effect, any of these events occurring on the wrong timescale ends not just a civilization or a species, but the entire experiment of life on Earth. This is not paranoia, it is geology. The Earth's fossil record contains the evidence of 5 mass extinction events, severe enough to eliminate the majority of species alive at the time. Life recovered from each of them, because life is resilient, and the planet remained habitable. But resilience is not invulnerability. There are scenarios rare, but physically possible from which recovery would not occur. An interstellar civilization is, by definition, immune to any single planetary catastrophe. The destruction of Earth, whether by asteroid impact or solar expansion or any of the other extinction-level events that cosmology and geology identify as possible, does not end humanity if humanity has established a self-sustaining presence around another star. The two populations, separated by 4.24 light-years, face entirely independent sets of existential risks. What kills one does not kill the other. This is the deepest argument for interstellar travel. Not curiosity, not exploration, not the discovery of fossils on a distant world. Survival. The survival not of any individual, or generation, or civilization, but of the lineage, the 4 billion-year experiment in organized chemistry that produced, among other things, the beings capable of contemplating their own fragility. There is a particular kind of hubris in assuming that the universe will continue to be hospitable to life on Earth indefinitely. The Sun will remain stable for another 5 billion years. In cosmological terms, this is an enormous span of time. In biological terms, it is an invitation to complacency. 5 billion years is not forever, and the events that could end life on Earth before the Sun expands are not all as improbable as the asteroid impact scenario might suggest. The only response to this vulnerability that is commensurate with its scale is to ensure that the continuation of life does not depend on the continued habitability of any single world. Becoming an interstellar species is not a luxury. It is, on the longest timescale that matters, a necessity. But necessities are not automatically achieved by being necessary. The history of human civilization is full of things that were clearly necessary and were nonetheless not done, or were done too late, or were done inadequately. Necessity creates the argument. It does not create the will, the consensus, the sustained commitment, or the sacrifice. The will must come from somewhere. It must be cultivated. It must be transmitted from generation to generation across timescales longer than any individual life, sustained by institutions and stories, and a shared sense of purpose that does not depend on any single political moment or economic cycle. This is what the great acts of human civilization have always required. The construction of the great cathedrals of medieval Europe took centuries. No individual who laid the first stones lived to see the completion of the building they began. The project was sustained by institutions, the church that existed across generations, and by a shared sense of purpose, the glory of God, the permanence of the faith that gave meaning to individual contributions within a project whose completion lay beyond any individual life. The interstellar mission requires something similar, an institution capable of sustaining a centuries-long commitment, a shared sense of purpose capable of giving meaning to individual contributions, the engineer who designs a component that will not be used for 50 years the politician who allocates funding for a mission that will launch after they are dead, the crew member who boards a vessel knowing they will not live to see its legacy fully understood. These are not small asks. They are in fact among the largest asks that any civilization can make of its members. They require a degree of identification with something larger than the individual self, larger than any single generation, larger than any particular nation or culture or political system. Whether humanity is capable of this level of sustained commitment, whether we can overcome the short-termism that characterizes most of our political and economic institutions and organize ourselves around a goal measured centuries, is genuinely uncertain. Our track record is mixed. We have achieved great things over long timescales when the institutional and cultural conditions were right. We have also abandoned great projects, fractured coalitions, lost the thread of long-term purpose in the noise of immediate crisis. The Interstellar mission will happen, if it happens, not because physics permits it or because the arguments in favor of it are compelling, but because human beings find in it something they cannot find elsewhere, a story large enough to contain their lives, a purpose whose scale matches the scale of the universe they have discovered themselves to inhabit. The universe, as we have come to understand it, is 93 billion light-years across. It is 13.8 billion years old. It contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars. It operates on timescales and at distances that make the entirety of human history, the full span of every civilization that has ever existed, vanishingly small. Against this backdrop, a species confined to a single planet around a single star, in an unremarkable spiral arm of an unremarkable galaxy, is a species that has not yet begun to live up to the scale of the universe it finds itself in. The journey to Alpha Centauri is the first step, not the solution to this asymmetry. No single journey could be, but the first acknowledgement that the asymmetry exists, and the first concrete act of response, the declaration that we are not content to remain small, that the universe is not merely a backdrop to our small planetary drama, but a place we intend to inhabit. This declaration will cost everything it costs. It will require the engineering and the sacrifice and the ethical reckoning and the sustained commitment across generations that we have examined throughout this journey. It will require people to give their lives to it literally, in the sense of the crew who will spend 42 years in transit, and figuratively, in the sense of the generations of scientists and engineers and politicians and ordinary people who will give their working years to a project whose completion they will not see. And it is worth it, not because the calculation comes out positive in any simple accounting, but because the alternative remaining on this one world, confined to this one pale blue dot in an immensity of dark, is a choice that the universe itself seems to argue against. We are the universe's way of looking at itself. We are organized matter, capable of measuring the distances between stars and understanding, in some partial but real sense, the processes that power them. This capacity for wonder, for inquiry, for the sustained and disciplined pursuit of understanding across generations is the most extraordinary thing we know of in the universe. It would be a strange choice to keep it confined to a single planet. Go outside tonight, if you can. Find a place away from the lights, away from the ambient glow of the city that washes out the sky and makes the stars seem fewer and fainter than they are. Drive out into the countryside if you must, or find a rooftop, or simply stand in a garden and let your eyes adjust for a few minutes until the fainter stars begin to emerge and the sky deepens from grey to black to something richer and more layered than any color has a right to be. Then find the Southern Cross, if you are in the southern hemisphere, or ask someone who knows the sky to point you towards Centaurus. And within that constellation, find the bright star, actually 2 stars, unresolvable to the naked eye, appearing as one that sits near the pointer stars of the cross. That is Alpha Centauri. You are looking at something 25 trillion miles away. The light entering your eye right now departed that system 4 years and 3 months ago. It has been traveling at 186,000 miles per second, without pause, without friction, without anything to slow it down, and it has only just arrived. The distance it crossed to reach you is so vast that even light, the fastest thing in the universe, required years to cover it. Hold that in your mind for a moment. Not the number, the reality behind the number, the actual physical emptiness that light crossed for 4 years before touching your eye. This is where we have spent the last several hours. Not abstractly, not in the comfortable distance of statistics and diagrams, but in the full weight of what that point of light actually represents. We have walked through the physics of getting there, the rocket equation and the radiation and the micrometeorites and the propulsion systems that do not yet exist. We have inhabited the vessel that the journey requires, the rotating habitat and the closed-loop life support and the nuclear reactors and the 42 years of recycled air. We have sat with the psychological reality of permanent isolation, the slow erosion of the self, the relationships forged and fractured in confined space, the children born into a world bounded by metal walls, the grief of a home that recedes beyond any possibility of return. We have stood on the surface of another world and found, in the ancient rock, the shadow of life that once existed there and does no longer. And we have asked, not rhetorically, but with genuine seriousness, whether any of this is justified, whether the cost in resources and in human lives is proportionate to what the mission achieves, whether the people who go can truly consent to what they are giving, whether humanity is capable of the sustained commitment that a centuries-long project requires. These questions do not have clean answers. They may never have clean answers. They are the kind of questions that each generation must revisit in the light of its own circumstances, its own values, its own understanding of what the universe is and what humanity's place within it might be. But there is one thing that has become clear over the course of this journey. One thing that the physics and the engineering and the psychology and the philosophy all point toward, from their different angles, with different languages, but with a consistency that deserves to be named. We are going to do this. Not tomorrow. Not in the next decade. Almost certainly not in the next century. The propulsion technology does not exist. The materials science does not exist. The institutional framework, capable of sustaining a centuries-long commitment, does not exist. The economic and political will, at the scale required, does not exist. None of this existed for heavier-than-air flight in 1850. None of it existed for nuclear power in 1900. None of it existed for the internet in 1950. The history of human technology is a history of capabilities that did not exist until they did, of problems that were insoluble until they were solved, of barriers that were absolute until they were crossed. The barriers between us and Alpha Centauri are real. They are not illusions, not failures of imagination that a sufficiently creative mind can simply think its way around. They are physical realities, the rocket equation, the speed of light, the biological fragility of the human body in deep space. We cannot wish them away, but we have, across the history of our species, developed a remarkable relationship with physical reality. We do not simply accept it. We study it, understand it, find within it the degrees of freedom that allow us to do things that were previously impossible. And then we do those things, not always quickly, not always efficiently, not always without enormous cost in lives and resources, but persistently, with a tenacity that seems, looking back across the full arc of human history, to be one of the most reliable things about us. The first human beings to cross the land bridge from Asia to the Americas, perhaps 15,000 years ago, had no map, no knowledge of what lay ahead, no certainty that the journey would not end in starvation or predation, or simply the failure to find anything worth finding. They went anyway. The Polynesian navigators who crossed the Pacific in outrigger canoes, guided by stars and waves and the flight patterns of birds, navigating to islands they could not see and had no confirmed knowledge of, they went anyway. The sailors who rounded the Cape of Good Hope, the explorers who crossed Antarctica, the pilots who flew the first transatlantic routes, all of them went into conditions they could not fully anticipate, sustained by a combination of preparation and will, and something that is difficult to name precisely, but that looks, from a distance, like an irreducible human need to find out what is on the other side. Interstellar travel is the next expression of this need, the largest expression yet attempted, the one that will require the most preparation, the most resources, the most sustained commitment, and the most sacrifice. But not a different kind of thing from what came before. The same thing, at a larger scale. The crew of the first interstellar mission, whoever they are, whenever they live, whatever propulsion system carries them, and whatever vessel sustains them, will be the inheritors of every exploration that preceded them. They will carry, without knowing all of its sources, the accumulated courage of every human being who ever stepped into the unknown, because the unknown was there and they needed to know what it contained. They will also carry something more specific. They will carry the knowledge accumulated over whatever centuries precede their departure of what the journey costs. They will have studied the psychology of isolation with a depth we cannot currently achieve. They will have designed their vessel with an understanding of long-duration spaceflight that makes our current knowledge look rudimentary. They will have developed governance frameworks and conflict resolution systems and cultural practices specifically tailored to the conditions of a 42-year closed environment mission. They will be better prepared than any crew has ever been for any mission in human history, and they will still be afraid, because preparation does not eliminate fear. It only ensures that fear does not eliminate preparation. On the day of departure, whenever that day comes, there will be a moment somewhere in the sequence of events that culminates in the vessel, leaving Earth's gravitational influence and beginning its long acceleration toward the stars, when each crew member confronts what they have done, when the reality of the commitment, not the abstract commitment, not the training room commitment, but the irreversible, physical, there is no going back commitment arrives in full. Some of them will feel it as terror, the kind of terror that constricts the chest and makes the hands cold, and floods the body with the ancient biological signal that something dangerous is happening, and escape is the appropriate response. Some of them will feel it as grief, the grief of departure, of the finality of goodbye, of the knowledge that every face they love will age and change and eventually disappear without them present. Some of them will feel it as something that has no common name, a kind of vast, still clarity that comes when all the alternatives have been removed and there is only the path ahead, extending into a darkness that is not threatening so much as simply immense and honest and real. All of these responses are correct. All of them are the appropriate emotional responses to a situation of this scale. The crew member who feels no fear is not brave. They have simply not yet understood what they are doing. Understanding comes later, in the long middle of the journey, when the novelty has faded and the reality has settled into the bones. Bravery is not the absence of fear, it is the decision to go anyway. We began this journey with a point of light in the southern sky. We have learned what it would take to reach it. The propulsion systems that do not exist but that physics permits. The vessel that would need to be assembled in orbit from the industrial output of a civilization. The 42 years of confinement and radiation and recycled air and psychological erosion, the governance challenges and the reproductive ethics and the communication delays that stretch a question and its answer across 8 years of time. The discovery at the end of it all that life arose there once, and that the universe is consequently larger and more generous than the conservative estimate suggested. We have learned what it costs, in resources that could have been spent elsewhere, in the lives of the people who go, in the grief of the people who stay behind, in the moral complexity of decisions that cannot be made cleanly. And we have learned why, despite the cost, it is something that we will do. Because the alternative is to remain here, to look at that point of light in the southern sky, and to know what it is, a triple star system, 25 trillion miles away, orbiting a world that once harbored life, surrounded by a darkness full of other stars and other worlds and other stories written in rock and chemistry and time, and to choose not to know any more than that, to be content with the light that reaches us without ever reaching back. That is not who we are. It is not who we have ever been. It is not, if the arc of our history means anything at all, who we will choose to become. There is a particular quality of the light from Alpha Centauri that is worth noting as we close. It is, in terms of color and intensity, broadly similar to the light from our own sun, warmer than Proxima Centauri's deep red, closer in character to what you would see on any clear afternoon anywhere on Earth. If you stood on a world orbiting Alpha Centauri A at the right distance, the light on your face would feel familiar. Not identical to sunlight, not quite, the spectrum would be slightly different. The shadows would fall at unfamiliar angles because the sky would be different but recognizable. Something you could call warmth without irony. This familiarity is not cosmically significant. It is a coincidence of stellar classification, nothing more. But there is something in it that speaks to the nature of the journey. We are not going somewhere entirely alien. We are going to a place where light, similar to ours, has been falling on rock and, once, on life. For as long as our own system has existed, we are going to a place that is, in the deepest sense, part of the same neighborhood, the same corner of the same galaxy, formed from the same population of stars, subject to the same physics, illuminated by the same fundamental processes. The universe is not in the end a place of infinite strangeness. It is a place of deep regularity, of laws that operate the same way everywhere, of processes that produce similar results from similar conditions across billions of light years. The life that once existed on Proxima Centauri b was built from the same amino acids as the life on Earth. The star that warmed it fused the same hydrogen as our Sun. The rock that preserved its fossils formed through the same geological processes as the rock beneath your feet. We are not alone in the universe. We were never alone. We are simply far apart, separated by distances that make connection almost impossibly difficult, but not, ultimately, impossible. That is the truth that the journey to Alpha Centauri teaches, not the specific truth about Proxima Centauri b, or about the fossils found there, or about the atmospheric chemistry that suggests the presence of an ancient biosphere. The deeper truth, the truth about what kind of universe we live in, and what kind of species we are, and what the relationship between those two things might eventually become. We live in a universe that made life. More than once, in more than one place, from the same basic chemistry, under different conditions, with different outcomes. A universe that is, in some sense, that is not mystical but purely physical, hospitable to the organization of matter into forms that experience and respond to and attempt to understand their surroundings. We are one of those forms. We are the form that looks up. And Alpha Centauri is 4.24 light-years away. The light from it is in your eyes right now, if you go outside and look. It left that system before most of the events you remember clearly. It crossed 25 trillion miles of emptiness to arrive. It has been waiting for you to look at it and understand what it means. Someday, someone will look at it from the other direction, from a viewport in a vessel that has spent 42 years crossing the space between, from the surface of a world that no human foot has touched, from orbit, watching the familiar constellations of home rearranged by the slight shift in perspective that 4.24 light-years provides. They will look toward where our sun is a point of light, unremarkable among the hundreds of thousands of other points of light in that sky, and they will feel, at the distance of 25 trillion miles, the full weight of what they left behind and the full meaning of what they have reached. And in that moment, in that specific and unrepeatable moment, humanity will have become something it has never been before, something that 3.8 billion years of evolution on a single planet could not have produced and cannot fully explain. Something that looks out from two places at once, from two stars, from two different angles on the same universe, and understands in a way that confinement to a single perspective never permits something true about the shape of the whole. That is worth the cost. All of it is worth the cost. Go outside tonight. Find that point of light. Look at it for a long time. The light you are seeing is 4 years old. It has been traveling toward you since before you can remember, crossing a distance that defeats every scale of measurement the human mind evolved to use. It asks nothing of you. It does not know you are there, but you know it is there. You know what it is, and how far it has come, and what waits at the end of the journey to reach its source. You carry, in your understanding of that small point of light, more knowledge of the universe than any human being who lived before the age of telescopes and spectroscopy and space probes, and the slow, patient accumulation of everything we have learned by looking up. That knowledge is the beginning of the journey. The rest is engineering and time and the particular kind of courage that belongs to people who choose to go anyway. The stars are not impossibly distant. They merely wait for us to become the kind of species that reaches them. And we are, unmistakably, becoming that species. Star by star, generation by generation, in the long, slow, irreversible movement of a civilization that has looked up at the night sky and decided, once and for all, that looking is not enough. Sleep well tonight. The light from Alpha Centauri will still be there when you wake.